Good morning. Welcome to the tutorial on the mathematics of deep learning. I'm sorry for the little delay, and I hope it will work out from now on. So I think we all know that back in 2012, there was a huge improvement in the performance of recognition systems, visual recognition systems in particular, thanks to the use of deep learning. And in particular, after a good 10 years where the performance was more or less stable, there was a 10% improvement back in 2012. And from then on is essentially history. In 2012, the performance went down from about 30 to 15. Then in 2013, it went down from 23 to 11. So here, blue is deep learning-based methods. Blue is non-deep learning based, and red is deep learning based. And from 2014 onwards, pretty much all methods that have been tried in the ImageNet are deep learning based. And the error went down from 15 to 11, then 12 to 6, and in 2015 it went down to 3.5% using a network with 150 layers. Just for comparison, back in 2012, the number of layers was about 7. So at the beginning, many of us thought, okay, this is maybe not true. Then, well, it is true, but true for classification. It's not going to work for other things. But quickly enough, people realized that you could transfer these from massive data sets to smaller data sets via transfer learning by just retraining the top layer and keeping the first few layers fixed as a feature extraction layer. Quickly enough, people figure out that it could be extended to recognition of faces. They figure out that it could also be extended to detecting objects, which was something that we did not anticipate. And today, basically almost every computer vision task, the best systems are based on deep learning, be it estimating pose, again, a very difficult problem, as well as semantic segmentation. Many of us work on semantic segmentation for many years. We condition random fields. And the performance of deep learning methods for that task is also significantly better. So it is natural to start thinking about why this might be the case. And when you ask the practitioners and the experts, the answers that are given typically are the following. One of them is that the features are learned and rather than handcrafted. If I had to think a little bit, that's true. Features are learned today. But maybe now what is handcrafted is the architecture rather than the features. Right? Because we really don't know how to design the architecture. It's really a trial and error process. Pretty much the same as feature design was 10 years ago. The second one is that more layers is better from a practical standpoint. And what this curve shows is the mean average precision on it. And the x-axis is the number of layers. So 3 to 13, so 23 in this particular case. The other reasons is that there is a lot more data than there used to be 10 years ago for training purposes, and that is what allows one to train bigger networks. It's not entirely clear either, because if you think about how many data points do I need in order to train an SVM that generalizes well versus training a deep network, the number of training examples typically grows depending on the type of classifiers, but it grows potentially even exponentially with the number of parameters that are supposed to be estimated. And typically today, the number of parameters in a network is way bigger than maybe the number of training examples. So why more data, of course, allows you to train bigger networks, but the kinds of networks that are being trained are way bigger than what the amount of data would potentially allow, at least according to classical theory. So what is the reason why this is working remains a mystery. Of course, much of what's happened is because, fortunately, stochastic gradient descent as well as backpropagation are very amenable to computing on GPU. So that allows one to do a lot of experiments more quickly. And naturally, that's one of the other reasons for the success. But there's been new techniques also for regularization, and new techniques that were very different from the traditional ones. Like if you think about the way we regularize SVMs, it's always been with weighted, putting some L2 squared norms on the weights. And the way that techniques such as dropout, drop connect, or even it is believed that stochastic gradient descent is a form of implicit regularization. But those techniques are very different from usual. It's like I take some weights, I randomly drop some units, I don't modify the weights that I've dropped, and I keep randomly selecting different weights at every iteration. So you will wonder why those techniques have good generalization properties, so that remains another mystery. In terms of modification to the architecture of the network, other than the fact that they're deeper versus 20 years ago, the other modification is the type of nonlinearity being used. If you look at the neural networks from 20 years ago, a natural nonlinearity that was used is this blue curve here, the sigmoid. And today, there is the use of these rectified linear units that just keeps the input feature with the identity above a threshold, and it zeroes out otherwise. The reason why people use this type of nonlinearity, the reason that is given by practitioners is what they call avoiding the vanishing gradient problem. What that means is that if you look at the sigmoid, the gradient is zero, it's nearly zero or very small in this region, and it is the same thing here. And so while the gradient of the sigmoid is the identity, so the gradient is backpropagated. So of course you could think that that's a necessary condition not to get stuck. But if you ask anyone who has done optimization whether there is any theorem that just because the gradient is non-zero, you're going to get the global optimum, that's not true, right? So this, to me at least, or to anyone with at least Calculus 101 on optimization, saying that the gradient is not vanishing is an unsatisfactory explanation as to why you might find a good local minimum. And so I think it's fair to say that while there's been a lot of research, and I'm going to summarize it recently, the understanding of deep networks remains very shallow. And so part of the goal of this tutorial is to provide some understanding as to what's the state of the art and what's the recent progress in the mathematical understanding of deep networks. So what are the key theoretical questions in the mathematics of deep learning? The first one is really how do we design architectures in a principled manner? The second one is how is it the case that even though the problem is very complex and large and non-convex, I can find good minimizers? And the third one is how is it the case that with a huge number of parameters and a small number of training examples relative to that, these networks generalize very well. Okay. So regarding the first question, architecture design, the kinds of questions that you would like to know is how many layers should I put? What is the size of every layer? What layer types do I pick? What functions can be well approximated by different type of nonlinearities or architectures? And what is the impact of the architecture in terms of the expressiveness of the network? Now, these questions, people thought about them 20 years ago or 30 years ago, and one of the most well-known results from the late 80s is the fact that if you take a network just with a single hidden layer, they are what is so-called universal approximators. Namely, they can approximate, in principle, any function. And the way that they achieve that result is by saying, if I just increase the number of neurons to infinity, then I can approximate any function. It's almost like, Taylor series, that if you add sufficiently many terms, then you can approximate. Okay, it's not any, of course. You have to assume that it's maybe continuous and a few technical assumptions. And so you would say, well, this means why do we need any complex networks? Why do we need many layers? It should be enough just to add more and more neurons, and eventually it should be able to approximate any input-output map. For those of you who are in the back, there is at least 7 or 8 seats here in the front if you want to come. So why is it working then? The theorems from the 80s sort of said that just a single hidden layer would work. So there is recent work showing that there are exponential gaps between deep and shallow networks, meaning that the number of regions that you can potentially approximate when the size of the network is fixed is significantly larger when you add depth to the network. Okay? There is also extensions of these universal approximation type of results from the case of networks with single hidden unit to what is called deep narrow Boltzmann machines. So the idea here is that you have very few neurons, but the depth is now increasing. And there is also work by Cohen in 2017 showing that you can relate the training of, you can relate the architecture and the input-output map of neural networks with the input-output map of hierarchical tensor decompositions. And last but not least, in fact, one of the first works that started a little bit of theoretical analysis was the work of Stefan Malat and Joan Bruna, where they studied the so-called scattering networks, and they try to understand stability properties. If I perturb a little bit the input, how much is the output perturbed? And in their case, they design networks that actually have fixed weights, and they are able to perform very well for some simple data sets, like MNIST, even though the network has fixed weights. They're not learned. Okay. So showing in a sense, and the reason is that they can prove this stability. That's one aspect. The other one is that they show that you can approximate deformations. So in a sense, demonstrating that what a network is capturing as you add more and more layers is invariance to deformations of the image. Okay. The second question is optimization. The problem is non-convex. So how is it the case that anything works? So the key question is, well, how does the error surface look like? Maybe there are lots of local minima, maybe not. Maybe there are many global minimizers and they're all equal to each other. Or maybe there are lots of saddle points. Regardless, are there ways of exploiting maybe it's a special type of function, and even though non-convex, I can still prove something about it. I can maybe have still guarantees of global optimality in spite of the non-convexity. And the other question is, why is it the case that local descent methods work very well? I mean, if you look at the core technology for optimizing networks, is really stochastic gradient descent. So what type of minima does stochastic gradient descent converges to, and why they happen to generalize well? It's a good question. So again, these questions were thought about more than 20 years ago. And people knew already back then that if the networks are linear, if you have no nonlinearity in just a single hidden layer, you can demonstrate that maybe there are lots of local minimizers, but all of them are global. Okay. What does that mean? Well, for the sake of simplicity and ease of understanding, think of just factorizing matrices, right? Let's say I find the optimal factorization. Let's say I do PCA. Everybody knows how to do that. You can always change the basis, right? And therefore change the pair of matrices that give rise to the same product. That shows that there is infinitely many solutions that are equivalent, and they're all global minimizers, right? So that's a little bit the type of result. So a linear network is really like matrix multiplication, really, okay, and factorizing matrices. And I'll show that why that's the case in a minute. But back then, people realized that convergence to global minimizers fail as soon as you add a nonlinearity. And the only cases they could demonstrate that things will work is that you assume that the data is linearly separable, which is sort of a little bit of a strong assumption, right? And much of the analysis was really done for networks with a single hidden layer, perceptrons in particular, and with sigmoids in between. So in the last 3 or 4 years, there's just been an explosion of work in this area. It started a little bit with the work of Joshua Bengio back in 2005, where he showed that convex. But more recently, there's been a family of works trying to understand the error surface. There's been connections made between optimization and problems in physics, particularly thin plate models, which in a sense, if you think about them, is like, I'm hand waving here a little bit, but what they are is, imagine fully connected dense networks with random weights, and then you analyze the error surface for those. So for those type of networks, they showed that the local minima tend to concentrate, tend to have very close values to each other. But again, I think the critique is that that isn't exactly the type of networks that are used, in the sense that they're not fully and densely connected, and not necessarily with random weights. The other type of work has been on this idea of entropy SGD, which is the idea that if you, interestingly, if you just take stochastic gradient descent and if you add noise and you perturb it a little bit, you can converge to better local minima than you would if you just do gradient descent, for instance. And the other work is the one that is at the very end, and that's primarily the one I'll concentrate here today, is essentially showing that if the networks are large enough, the problem becomes easier. In fact, all of the spurious local minima disappear, and you can have guarantees of convergence to the global minimizers. The third question is how well networks generalize to new data. So critical to that, typically, has been the fact that if you don't regularize the weights, the networks overfit. Namely, they perform very well in your training examples, but not so well on new examples. So to prevent overfitting, you have to design a regularizer. And in the old times, that would be L2 squared, or weight decay. But today is dropout and a variety of other things. And so if one knew what the boundary looks like, and if the boundary was simple enough, then small modifications to the boundary wouldn't change the performance of the network a lot. But if the boundary is very complex, then tiny perturbations mean that the performance can dramatically be changed. So how to prevent that and how to design regularizers that result in simple boundaries, it's a key question. So again, the work from the 80s showed that the number of training examples needed in order to achieve good generalization grows exponentially with the network size. So by that standard, none of the networks today should be working because the number of images is less than the number of parameters. So this has motivated these techniques of, well, people have observed this weird phenomena. If you're just doing the optimization, if you stop before getting to the global minimum, sometimes performs better than if you wait until convergence. The other one is this idea of not updating all the weights. I just update a small fraction, and the next iteration I update another fraction, and that's the idea of dropout. And now people are starting to speak about this idea of implicit regularization, namely that the optimization algorithm itself performs some form of the regularization, except that it's not exactly clear what it is. So that has motivated a lot of work in the last 2 or 3 years, saying, in fact, one nice title that came out recently is called Rethinking Generalization for Neural Networks, where rather than the traditional view of putting some norms on the weights, the idea is really that maybe there are many possible optimal solutions, and that the goal of the regularization should be to pick among those that generalize better. And one type of regularization that has shown up is this called path stochastic gradient descent, that really tries to take, given an input and given an output, what are the possible paths to the network that connect those, and that's a collection of weights. And then I just take multiplication of those weights, and then I sum over all the possible paths connecting that input and that output. And that has led to these products of weights type of regularizers that are very different from usual. And there is a lot of recent work on showing generalization bounds for these type of regularizers. Okay. Now, though I've presented these three aspects of theory as three different things, they're clearly interrelated. In fact, I already mentioned a few such things. Optimization can impact generalization. As I just said, maybe stopping early is a good idea. We don't know why. But that would impact how well the network generalizes. Of course, the network architecture has a big effect on generalization as well. If I have a very shallow network versus a wide network, what kind of functions can be approximated? That is important to generalizing well. And last, and this is maybe the main topic of the first talk, this is going to be that some architectures might be easier to optimize than others. Okay? And so the three problems are very much interrelated, and there is a lot of need for research at the intersection of the three. So this is what motivates this tutorial, trying to answer questions about how we should design the architecture, about how well these networks generalize and why they generalize well from fewer training examples, and also about the optimization, how we can guarantee global optimality for these networks. So I'll begin by speaking about the optimization part, and that would be the first 45 minutes. Then Raja will continue speaking about generalization, about the input-output maps and why they can approximate lots of functions, why do they separate data from different classes and bring together data from the same class. Then we'll have a coffee break for 45 minutes, 10:15 to 11. And then Raja will continue. Unfortunately, Joan Bruna couldn't make it today, so Raja will give two talks. The second one will be about generalization bound. And the last talk of the day is an invited speaker, a recent work of Miki Elad and his student Vardhan Papian, who will speak about the connections between convolutional neural networks and sparse coding, or a particular form of sparse coding called convolutional sparse coding, and recent theorems as, in that area. So the tutorial schedule and slides will be available in my website. So you just go to my website, activities, and then you will see the tutorials, and you'll find the ICCV tutorial. In addition, there is a sort of tutorial style paper by Joan, Raja, Stefano Soato, and myself that will appear in the Conference on Decision and Control later this year. So that will summarize and will have all of the references on the theory that have appeared in the last few years. So are there any questions before I get started with the first lecture? I insist for those of you who are standing in the back that there are a good number of seats here in the front. I see 1, 2, 3, 4, 5 at least. Okay, so this first lecture will be about the question of optimization. The problem is non-convex, and how is it the case that it works? Can we have guarantees of global optimality, and so on and so forth. So why is it a non-convex problem? So what is the nature of the optimization problem? So mathematically, this is more or less how a neural network works. So we begin on the left with the input features. That can be an image, audio, this computer vision. So let's say it's a collection of images that come as the input. And the first thing one typically does is to apply a linear transformation to it. So let's say that that was a convolutional layer. And the notation here is going to denote the fact that convolution is a linear operator, so I can always represent it somehow as matrix multiplication. So think about x1 as the matrix corresponding to convolution. But it could also be a fully connected layer. In that case, it is the matrix directly. So x1 is going to denote effectively the weights of the first weight layer. And then, typically, there is a nonlinearity that is done. In the old times, that was that blue sigmoid. Today is the rectified linear unit. But there are other forms of nonlinearity. You could do max pooling, you could do normalization, and so on and so forth. Then, when you go to the second layer, you repeat the process. There is another linear transformation, and then there is another nonlinearity. And you do this k times, where k is the number of weight layers. So the output of the network here, right before predicting the label for that image, is therefore, I'm going to denote it with this function phi, and the function phi is going to be a function of the weights of the layer. So x1 for the first layer, xk for the first layer. Notice that I am not explicitly writing that this is a function of the input image here, which I denoted by v. The reason being that in this analysis that I'm going to be presenting, the input is thought to be fixed, right? I've got a training set, and that is fixed, and that is input to the network. So the variables of the network are just the weights, and we're going to be optimizing over the weights. So that's why I'm going to write function of just the weights. So what is the optimization problem? The optimization problem is that you're given also a set of labels, y, and you want to compare the labels to the predictions by the network. And the predictions is this phi map that I just talked about. Okay. So how close the prediction of the network are to the given labels, and the closeness is measured by some laws. Typically, there are many losses that are used, but the simplest one is the square loss, so the sum of the square of the errors on the labels here. So that's the first term. The second term is the regularization term. So theta here is some function of the network weights. The simplest, again, is the sum of the square of the weights, and that's the weight decay function. And lambda is a parameter that just trades off between fitting the data well and regularizing the parameters. Okay, so this is the optimization problem I'll be talking about, and it will be, unlike many other settings recently, is deterministic. So the weights are not random, the input is not random, I'm not making any assumptions of that kind. So it's a very traditional optimization problem in that regard. The input is fixed, the output is fixed, and I just optimize over the weights. Okay? So how are networks optimized these days? So the traditional method is gradient descent that leads to backpropagation. And today it's done in a stochastic manner using stochastic gradient descent, that instead of taking the whole data and computing the gradient of the whole function, you just take small pieces of the data called mini batches and just approximate the whole gradient by the gradient in a small piece. And at every iteration, you just change which batch of the data you pick. And that's stochastic gradient descent. So to get to a good local minima, because one can use many initializations, one approach is to just run this many times and pick less. In fact, typically you can just look at how fast you're going down. And if you're not going down very fast, you can throw away that initialization. And repeat this process multiple times until you find a good minimum. But there are some mysteries. One mystery is that it could be the case that you as a faculty give the same problem to two different PhD students, and they train the network and they come back with very different weights. Right? Yet the performance they get is about the same, sort of suggesting that maybe there are multiple local minima that are about the same in performance, or perhaps even maybe they're equal. Okay. In fact, the objective values might not be dramatically different, yet the network weights could be very different. There's been evidence also that rectifying linear units work better in practice than sigmoids, and the argument given, as I said earlier, is that they don't get stuck, namely they don't suffer from the vanishing gradient problem. And another observation that's happened is that when you have large networks, it could be the case that some weights are zero, and they call these dead units type of phenomena. And why this happens is not entirely clear. So what I'll be talking in this lecture is about optimization, but it's not fully unrelated from the other two. Yes?
So can you put the microphone a little closer?
Okay.
Because of the air conditioning.
Ah, okay. Is it better now or no? Is it better now? Okay, sorry. Okay, so while I'll be speaking about optimization, the deal is that the architecture will play a role. And in fact, there will be two properties of the architecture that will play a role in getting guarantees of global optimality. The first one is this property here that I named positive homogeneity, that if you know what it is, fine. Otherwise, I'll spend a good 10 minutes explaining what it is. Okay. The second property of the architecture that facilitates optimization is the idea of having parallel subnetwork structure. Okay? And I'll explain also what that means. The second aspect is that there are properties of the regularizer that also make the optimization problem easier. One of them is using positively homogeneous regularizers, and I'll explain what that means. But the second one is the most important. If you use weight decay, that's a fixed regularizer. It doesn't depend on the data at all. So the idea is that we should be using a regularizer that adapts to the data and adapts to the size in particular. And so a big message that will come out of this talk is that if we want to guarantee global optimality, we shouldn't be thinking about networks of fixed size, but rather we should also adapt the size of the network to the complexity of the data, so that simpler problems may require smaller networks and complex problems might require bigger networks. Okay. So the type of results at a very high level that we will have are of the following flavor. We'll make some assumptions on the loss, and the assumptions that we'll make is that the loss is convex on the second argument. Okay? Wait a minute, didn't you just tell me that the problem is non-convex? Okay. So are you just assuming that it's convex now? No. So I repeat the assumption. Is convex on the output of the network. Okay. That does not mean that it's convex on the weights. So it's convex, if you wish, on this phi function. So think about the square loss, right? It's convex on the, in fact, it's quadratic. It's strictly convex, differentiable. You couldn't ask for a simpler function. Once differentiable is the second assumption. Again, L2 square is twice differentiable, so that's not a problem. L1 might be a problem. Okay. So this first set of assumptions is very mild. The second set of assumptions is that we're going to assume that the input-output map of the network is positively homogeneous. Here's the definition, actually. It means that if you scale the weights by some alpha, here, each weight is scaled by alpha, then the alpha comes out raised to some power. I'll show in a minute that this property is also mild. In fact, here's a list of functions that are homogeneous. ReLUs are homogeneous, max pooling is homogeneous, linear transformations are, matrix products are, deep networks with many layers that use combinations of these things are also homogeneous. And the theorems will be of two flavors. The first one is that if you have networks with parallel structure, and if you vary the size, namely you add many more networks in parallel, eventually you will get to a situation where all of the weights associated with one of the subnetworks is 0. And if you're able to find a local minimum such that all of the weights of a subnetwork are 0, that is also a global minimum. Okay? And I'll explain why that is the case. The second theorem is that even though, in principle, the landscape of the optimization problem could be very complex, in fact, observe here, there is an isolated global minimizer here, but here there is a valley of global minimizers that are all equal to each other. Okay? You can also have flat regions in between. You can have global maximum. You can have here potentially local minimum as well. So what theory predicts is that these local minimum actually disappear when the network is big enough. What I mean really is spurious local minimum. By that I mean minimum who are not global. Okay. So that's exactly the theorem, that if the size of the network is big enough, a local descent strategy, not necessarily gradient descent, in fact a fancier version where you modify the size, can find that global minimizer from any initialization. Okay. Again, these are all analysis type of results. I'm not saying that this immediately means that you've got a super efficient algorithm that will be able to implement this. In fact, I'll present a meta algorithm, but I'll argue, in fact, that some computations might be NP hard in between. Okay? So computational aspects are still being worked out. So this is the outline of the presentation. I'll begin by introducing these properties of positive homogeneity and the architectural property. Then I'll talk about the regularization, and then I'll take the time to explain these two theorems that I just mentioned at a very high level. Okay. Property number one. What is this positive homogeneity property? So the idea is the following. Suppose that I start with a network like this one. And all what I'm going to do is that I'm going to scale the weights by some factor. And that's what the alpha is here. And I'm going to assume that the scaling is non-negative. Okay, that's all. So as it turns out, if I do that, the idea will be also scaled, as you can see. So instead of having the output y, I'll have an output alpha to the p times y. So mathematically, this means that this was supposed to be the input-output map, and I just scale it, and now I have alpha to the p. And that property is called homogeneity in general. The fact that I'm requiring the scaling to be non-negative is what makes it positively homogeneous. The p here is the degree of homogeneity. Okay, what is p typically in networks? Are networks typically homogeneous or not? So let me begin with the simplest function, just one neuron here. So what happens if I have a rectified linear unit and I scale the weights here? I'm going to multiply them by alpha. Well, this is just linear combination of weights, right? So the output is going to be scaled by alpha. It's just a linear operator. If I scale the input, I scale the output. So now the rectified linear unit comes in. So the z now is multiplied by alpha here. And now I need to take the maximum between that and 0. But because the alpha is non-negative, right, that doesn't change the sign of z. And so I can actually take the alpha outside. Okay? And so a linear operation composed with a rectified linear unit is homogeneous, and the degree is 1, because it's really like it's not a linear function, but from that perspective of scaling, it's like a linear function. I can take the alpha outside. Okay? So rectified linear units and linear functions are already homogeneous of degree 1. Let me take a slightly more complex network now with many layers. So again, let's do the same game. I'm going to scale the weights of the first layer by alpha. Because the first layer just has convolution, it's a linear operation, and has a ReLU, I already showed you that convolution and ReLU scale the output by alpha. Okay? So let me now repeat the process again. I'm going to scale the second weight layer by alpha. Because the input already was scaled by alpha, I'm going to get alpha squared. Now I'm going to do max pooling. So this means that every input to the maximum is scaled by alpha squared now. And I need to take the maximum between two things. Each one of them is scaled by a non-negative quantity. What that means is that I can take the alpha squared outside, right? Because it's non-negative, it doesn't matter. The maximum between the two, which one gives the maximum will not change. And the value will just be scaled by alpha squared. So that means that a max pooling layer just preserves, and so the alpha squared goes to the next layer. And finally, if I scale the last layer again, and it's a linear, then I'll get alpha cubed. So what that means is that this simple network that just has convolutions, ReLUs, max pooling, is homogeneous. And look at the degree in this particular case is 3, and that's exactly the number of layers that you effectively have. So typically, in fact, each layer of weights will increase the degree by 1. Okay. So that's I think the first message, that not all networks, but many of the simple ones are already homogeneous. And in fact, the degree of homogeneity is just the number of weight layers. Okay. So this is true beyond what I said for convolution, reuse, max pooling, linear layers, min pooling, max out, and many other possibilities. But notably, it's not true for sigmoids, okay? And so because in a few minutes I'll have these theorems that homogeneous networks, you can have guarantees of global optimality, this may be the first explanation as to why rectified linear units is better than sigmoids. And the reason is that they are positively homogeneous, and that allows you to have theorems of global optimality. Now, the theorems are sufficient conditions, so it doesn't mean that you have to have them, right? Notably, batch normalization also doesn't satisfy this property. In a sense, it sort of it does, but it resets the degree if you think about it, because it normalizes, right? So you increase by alpha cube, but then you reset it to 0. Okay, so that was the first point, that networks need to be positively homogeneous, but I hope to have convinced you it's not a super strong assumption, and many networks already satisfy that property to begin with. The second thing we're going to do is this parallel network substructure. So what does that mean? That from an optimization perspective, and this again can be in conflict for generalization, this may not be the case. Networks with parallel substructure facilitate optimization. So here's one example. A network with a single hidden unit that has lots of neurons in the middle. They're all like the same structure repeated over and over. And the core structure is that a single neuron with maybe multiple inputs, multiple outputs, and say ReLU. So by parallel substructure, I mean exactly that you take a subnetwork, in this case a single neuron, and just you repeat it many, 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 many times, and that's what's done here, and then you add them up at the end to produce your outputs. Okay. So this is a trivial example, but you can construct more complex cases, right? So pick now any network you want with maybe lots of layers, okay? And that's what is going to be our subnetwork. And let's assume that it's homogeneous so that it satisfies the previous property. So what we're going to do now is put many such networks in parallel and add them up, okay? So therefore, the idea is that the network is really the sum of positively homogeneous subnetworks. Okay? Is that clear? Now, you could go fancier and say that your subnetwork is the whole AlexNet, which is not exactly homogeneous, but it's almost homogeneous. And now you put many AlexNets in parallel, and you add them up, and that produces the output, okay? So this is exactly the notion of parallel subnetworks, and the notion of size, every time I speak about size, is going to be exactly the number of parallel subnetworks that you consider. So going back here, what is the size of this network? In this presentation is going to be the number of neurons in that layer. But when I go to this case, it's not going to be the number of neurons, it's not going to be the number of layers, it's really the number of parallel subnetworks. Okay. So that's an important restriction, and the full understanding of how to extend this to number of layers and number of neurons everywhere is still an open problem. We can only handle this parallel substructure for now. Okay, so that was the architecture part. They need to be homogeneous, they need to have parallel substructure. Let me now move to the regularizer. So this is the classical way that networks were regularized in the 80s. You just take the weight layer, sum of the squares, plus sum of the squares, plus sum of the squares. Sum of the squares of all weights of the network. Okay? Now, what kind of regularizer is this, thinking about the homogeneous property? Well, it is actually homogeneous, right? If you scale the weights by alpha, the regularizer is scaled by alpha squared, okay? So it's a regularizer of degree 2. But this network has actually 3 weight layers, and so the input-output map of the network, I convinced you that it was also homogeneous, but it's homogeneous of degree 3 because there are 3 weight layers. So it's important to note that regularizer and network are both homogeneous, but the degrees don't match. One is of degree 2 and one is of degree 3. Okay? So I'm not getting into the details, and that is in the paper indeed, but bad things happened when these numbers don't agree. In particular, you can show that if the degrees are different, then there are spurious local minima. You can always construct. So this is suggesting something mysterious, because people went into not using weight decay because they said it didn't generalize well, it didn't work as well, and that's why was maybe one of the motivations for using dropout or saying that stochastic gradient descent is a good regularizer. So what this theory is predicting is that you should adapt the form of the regularizer to the form of the network. And so if you have a network with 3 layers, you should be using a regularizer of degree 3. If you have a network with 150 layers, you should be using a regularizer of degree 150. And so weight decay is not going to work if you have a network of 150, and you can make it fail by having a lot of spurious local minima. All right? So, okay, so that's the first point. The regularizer also needs to be homogeneous, and it needs to have matching degree with the degree of the network. The second aspect about the regularizer is that it really has to be a measure of complexity of the network. Namely, small networks should have smaller regularizers, and bigger networks should have bigger regularizers. What do I mean by that exactly? So we're going to take a network, such as this one, and we are going to first just take one of the subnetworks. And in this particular case, there are 5 weight layers, x1 through x5. And we are going to define a regularizer just for that subnetwork alone. What properties are we going to require of this regularizer? 2. The first one is that it's non-negative. I guess it's not too much strong of an assumption, right? Weight decay is non-negative by construction. But the second one is that it's positively homogeneous of the same degree. So a property I already explained, and we need it to prevent bad things from happening. Okay? So what might be an example, in fact? An example is just take the weights from the first layer and take a norm and multiply the norms across the layers. Mysteriously, this product of weights idea is the idea that in the last 3 or 4 years, people are saying that's a good regularizer with good generalization properties. And I think Raja will describe why that is so in his presentation. Okay? But this is an example of what I'm talking about, what regularizer you could use. If you scale by alpha, the first layer, the second layer, you know you're going to get alpha to the 5th in this particular case. Okay? Okay. So that's going to be the regularizer for a single subnetwork. What do we do with the multiple parallel subnetworks now? We just sum them up. The regularizer for the whole network is the sum of the regularizers for each one of the subnetworks. And so R here is going to be the size and is the number of parallel subnetworks. And so the idea also is that we are going to be optimizing with a variable network size, and so we're going to be varying R, and the idea is that by adding an extra subnetwork, I increase the capacity, but I also increase the regularizer. So the regularizer really is trying to constrain the number of networks. In other words, it's trying to say, can you fit the data with the smallest possible number of parallel subnetworks? To make an analogy with matrices, is given a matrix, can you factorize it with a matrix of the smallest possible rank? Okay. And now in PCA, it's like model selection. I'm going to vary the rank and just pick the one that gives me the best fitting, but I also want that rank to be the smallest possible. That's going to be sort of the key idea behind it. Okay. So to summarize, the regularization properties we want is that the regularizer must be homogeneous and that it needs to adapt to the structure of the data. So let me now move on finally to the theorem. With those properties of homogeneity, parallel subnetworks, and adapting regularizers, what can you show? And interestingly, the results are applicable not only to
neural networks, but they apply to simpler problems, one of them being matrix factorization. And the explanation of the intuition, why it works and things like that is much easier to grasp if I just talk about matrix multiplication. So that's what I'm going to do first. I'm going to tell you why this is true for matrix factorization, and then I'll tell you how that generalizes to neural networks. Okay? So, matrix factorization. One way of factorizing matrices is actually not to factorize them, but just do this matrix approximation part. And that's sort of called convex formulations of the problem. So you give me a matrix Y, and you want to find a matrix X that is close to Y, and at the same time is, for example, low rank. And one way of encouraging that it's low rank is maybe with the rank itself or with the nuclear norm. I'll explain what that means in a minute. This is the case for many matrix completion works that way. Robust PCA works that way. And very nice because it's convex, we can find the global minimum. The problem is that the matrix you're optimizing can be large, and you don't have this structure on the factors that might be useful. So that's why in practice, many people work with factorized formulations. So again, if it is low rank, instead of optimizing over a gigantic matrix, I can directly optimize over the factors. And that's going to make the problem much smaller. The drawback is that now the problem may become non-convex. In fact, we've known this in computer vision for a very long time. People forgot that we used to do geometry and structure for motion in the past. And so this was factorizing the features into the shape and the motion matrices. And we were very used to alternating, given the shape, find the motion, and given the motion, find the shape, and things like that. And we were used to saying, well, after 3 iterations, this works out. But we knew it was non-convex, and we didn't know why we would be getting good local minimizers. But then you would get good reconstruction, so we were happy. So the problem is non-convex, and alternating minimization was the favored method in the past. Today, you wouldn't do alternating minimization. You would do stochastic gradient descent for large problems, right? Okay, so I've convinced you hopefully that there are 2 ways of tackling the problem, the convex way and the non-convex way. And the idea is, can we use insights of the convex to prove stuff about the non-convex? Okay, and that's exactly what we're going to do. And let me start by doing so with the nuclear norm in here. What is the nuclear norm? If you've never seen it in your life, is take the matrix, take the singular values of that matrix, and add them up. So it's the sum of the singular values. Unlike the usual Frobenius squared norm we use, which is the sum of the squared of the singular values. Okay? So that's what that norm is. Okay? And it's supposed to be a proxy for the rank. So in a sense, if the matrix has low nuclear norm, then it has low rank. And has been heavily used, for instance, to solve the Netflix challenge in matrix completion. So it turns out that there is this way of what is done. Take X, find any factorization of X that you want, UV transpose. That factorization may not be unique. I can do a change of basis, I can put a matrix here in the middle. Okay. Among all possible factorizations, select the one that minimizes the sum of the product of the norms of the columns. I repeat what that is. Sum from 1 to R. R is the number of columns of U, of the 2 norm of the ith column of U, U sub I, multiplied by the norm of the ith column of V. Again, I repeat, you minimize the sum of the products of the norms. Okay. And if you do that, you get back the nuclear norm. Okay. So what this suggests then is that, well, here I've got this theta that I didn't tell you what I was going to use. And you would have said here, well, you just substituted. You took X and you put UV transpose. Why don't you just take X and you put UV transpose? Then the problems are equivalent. But you know, the UV transpose already is going to make it non-convex, and then with a non-smooth thing is a little bit nasty. So instead, what I'm going to do is I'm going to pick this, and I'm going to put it there. Okay? So what is the relationship between the convex and non-convex? The lost piece is just a substitution. But for the regularizer, I'm substituting it by this fancier form, sums of products of norms. Now I can become even fancier and say, well, why the 2 norm? Why don't you pick anything else? In fact, in many applications in computer vision, this will be relevant. Say if X was a video, your factorization U times V, U might be the eigen images, so a spatial part. V might be the temporal dynamics, so that might be the temporal part. So you might want to say, well, for the images, I want to use total variation is my regularizer instead of the L2 norm. For the coefficients, for the dynamics, maybe I want it to be sparse or, you know, whatever. And so what this is saying is, what if you use L2 and total variation and L1 or any norms you want to put there to become fancier? So as it turns out, this process that I talked about here, you still get some function of X. So bottom line, there is a norm on X which is equal to the minimum of the sum of the products of norms on the factors. What does this mean in neural networks? It means that you have the output of your network. That's what this X means here. And the norm of the output of your network, there is a fancy norm on the output of your network that is equal to some minimization over all the network weights of products of weights, effectively. That's what I'm trying to say. And if that was the case, the beauty of this is that in the output space, this is convex because it's a norm. All norms are convex. And that's exactly the gist of what's going to allow us to say, well, this thing is non-convex and it's hard. But there is an equivalent convex problem, not equivalent, but very closely related, that I can analyze, and I can guarantee global optimality. And hopefully, I might get lucky, and that will induce some global optimality for this. So that's the gist. And that's actually exactly what happens for matrix factorization here. And here is the theorem, stated with more details. So for matrix factorization, assume that you have a loss function is convex on the second argument and differentiable. Suppose that you minimize this objective with your favorite technique, so be it gradient descent, be it alternating minimization, whatever you want. Suppose you were to get very lucky and you find a local minimum. Okay. So what this theorem says is the following. If you have a local minimum of the non-convex problem, okay, and that local minimum happens to be such that one entire column of U and the corresponding column of V are identically 0, then that local minimum is a global minimum. Okay? So factorizations with 0 columns are global minimizers. In addition, if you take the product of those 2 factors, that will be a global minimizer for the convex problem. Okay? That's what the theorem says. And pictorially, this is my picture associated with it. What's going on really is that we are also varying the size of the factorization, which is nothing but the number of columns. And as we're going to see, we can make it bigger and bigger and bigger. Eventually, you have a redundant representation. And so one column can be set to 0 without changing the factorization part. But adding an extra column would increase the regularizer. So that's why you're going down first, because you reduce the loss and you increase the regularization. But eventually, you cannot further reduce the loss, and you just increase the regularization. So that's why you find the global minimum. For those of you who are curious as to why in the world this is true and how you can prove it, the proof is long, but there are 2 key one-line insights into the proof. The first one is that the convex problem gives a global lower bound for the non-convex. Why is it so? Where does that come from? Well, here I said, right, the nuclear norm is equal to the minimum of this, and I'm going to use this as a regularizer. When you do that, when you replace this for a particular U and V, which is not the one that gives the minimum here, you get less than or equal to. because the loss is equal to the loss, but the regularizer is less than or equal to this other regularizer. Okay, so in words, in one line, the convex problem is always below the non-convex. But as it happens, at the global minimum, they're equal. Okay, and that's what the second line says, and that's exactly at the core of the proof. What we do is that because this guy is non-convex, you can always write down first-order conditions for global optimality. Okay, if this was differentiable, you know, the derivative is equal to 0. For the non-convex, you also write your first-order conditions, but you're not sure if it is a global minimum or not. So it turns out that you take that local minimum, you substitute it in the conditions for global optimality of the convex, and they are satisfied. So that's why it's a global minimum for the convex first. And because the convex is a lower bound, it's also a global minimum for the non-convex. Okay. So that's the first theorem. The second one is this theorem that if the number of columns is large enough, you can reach the global minimizer from any initialization. So what is the gist of this? The gist of it is the following meta-algorithm that tells you, in fact, how to find the global minimizer. So for matrix factorization, let's say you start with, let's say the matrix was rank 2, but you started with rank 1, so you don't know. So we start here, and we go down, and we go down, and we go down with gradient descent, let's say, and I get here. And let's say that I reach a local minimum. Okay? Then I ask, is theorem 1 satisfied? Namely, is one column of U and V equal to 0? The answer is going to be no, because I have not found the global minimum yet. So this is what I'm going to do. I'm going to increase the size from 1 column to 2 columns. And so I'm going to take my initial column and I augment U with 1 column. I augment V with 1 column. And this process is going to be equivalent to sliding that flat plateau from the left side to the right side. Okay. And once I get to the other side, I will start going down again, and I'll get to the global minimum. Okay? So what is this meta-algorithm, and why do I call it meta-algorithm? The meta-algorithm, the intuition is progressively increase the size, check for global optimality, and if not, you keep increasing the size. Eventually, one column would be identically 0, and once you get there, you know that you're at the global minimum. Why is it a meta-algorithm and not an actual algorithm? Well, there are two things here that are very difficult. The first one is, I told you, is like find a local minimum. Is that easy for a non-convex problem? No, that's a very, in many cases, can be an NP-hard task. So finding a local minimum is already hard. The second one is this thing that I mentioned easily, which is you just augment the size. Well, if you are naive about it, if you just increase, you know, this is like adding extra weights in the network. It's like adding a parallel subnetwork and initializing the weights for that extra subnetwork that you've added. If you're naive and you initialize them at random, you could start going up in the objective. So you need to pick what is known as a descent direction so that you really go down. So you need to choose these extra columns cautiously. But choosing a column that is guaranteed to go down is also an NP-hard problem, depending on what regularizers you pick. In some cases, it's trivial. For matrix factorization with 2 norms, it's an eigenvalue problem, finding the extra U and V that you need to add. But in other cases, it could be hard. So that's why I call it a meta-algorithm, because to implement it, there are 2 aspects of it that could be very complex. Okay. Let me give you a few examples of problems that many of you might work on, even if you're not in deep learning, for which this is useful. So non-negative matrix factorization, heavily used for phase recognition. You take phases, you do eigenphases, that's what the U is, and V is the coefficients. And because there is images, you want both of them to be non-negative. NP-hard problem, traditionally solved with alternation without guarantees of global optimality. So what our theory predicts is that if you modify the problem a little bit by adding this regularizer, which is sum of products of norms, and if you also optimize over the size of the factorization, namely the number of eigenphases is also variable, okay, then now you can have a guarantees of global optimality for this variation of non-negative matrix factorization. A second example is dictionary learning, heavily used in image denoising. It was also used a lot before deep networks. This was being heavily used for classification as well. So you're given a set of data, image features, and you want to express it as a linear combination of atoms in a dictionary. That's the U. V is the coefficients. And you want the coefficients to be sparse, so this is what expressed here, the number of non-zero entries of every column of V less than some threshold. Again, people used to alternate K this is a new factorized formulation where, again, what we do is simply add a regularizer to the problem. What regularizer? For the U, which is the dictionary atoms, we just have the L2 norm, sort of having the typical constraint that you want the L2 norm to be equal to 1. For the sparse coefficients, we have the L2 norm as well, but then we have the L1 norm, which is sort of the typical penalty for sparsity. Okay? So this is a new formulation of dictionary learning for which you can have guarantees of global optimality. Robust PCA was another popular method for around 2010, where the idea is that I've got a matrix that is supposed to be low rank, and I just corrupt a number of entries, a small fraction, so a sparse part of it. And so this is written here in this equation. The given matrix is equal to a low rank part plus a sparse part. And to find the original low rank and the original sparse, what I'm going to do is minimize this objective, where this is the nuclear norm of X, sort of penalizing the rank of X. And this is the L1 norm of E, which penalizes make it sparse. Right? So if you take this problem and you eliminate E, you immediately get this loss plus regularizer type of framework. Okay? So given matrix Y, find a matrix X that is close to it as measured by the L1 loss and make it low rank. So you would say, okay, immediately I can have a factorized version of it where instead of solving for a gigantic matrix when Y is very large, I'm just going to solve for the factors. And I'm going to penalize, instead of the nuclear norm, I'm going to use the sum of products of norms, which is what we seem to be liking here. So unfortunately, it's not as easy. Our theorems fail in this case. The reason they fail is because the loss being chosen here is the L1 loss, which is not differentiable. Okay. But you can make a tiny modification where instead of having you add an extra term, which is dense noise, that you penalize with the Frobenius squared. And now you have the L1 loss here. The typical regularizer, this is the same as that. And this is, the data must be equal to the factorization plus some error. Okay. And once you do that, the loss is now differentiable. And essentially, it's like you move the L1 part from the loss to the regularizer, because the regularizer is happy to have non-smooth things, but the loss is not. That's all. So by playing around, now you have a factorized version of robust PCA, which is non-convex, but you can have guarantees of global optimality. Okay, so the summary is, for matrix factorization, you can have guarantees of global optimality, and the way you do that is vary the size, which is the number of factors. And if one column is 0, you get a global optimum. How does this extend to neural networks? So let me first talk about networks with a single hidden layer. So this is the number of inputs, this is the number of hidden layers, and this is the number of outputs. Let's assume it's fully connected. So the weight here is D1 by R. D1 is the number of inputs. R is the number of hidden layers. So in this particular case, if you think about the input-output map, it's just V multiplied by X and then multiplied by X2 transpose, and there is this nonlinearity here. So this is really if there was no ReLU, this is just matrix multiplication. Okay, so it's the same problem as before. So it's the same problem as before with a nonlinearity. The case of multiple parallel subnetworks I spend a lot of time talking about is also homogeneous, it satisfies. So the key thing I need to tell you is how this regularization stuff from matrices extends to deep networks. And here's how it goes. So for matrices, what we said was take the output, factorize it, and among all possible factorizations, choose the one that minimizes sum of products of norms. And that gives you a convex function on the output. And as soon as I have a convex function, I'm in business. How do we extend this to deep networks? The idea is the same. Take X here, which is the output of the network, for some particular choice of weights. Okay, so I have K layers now. Phi is the map, and that gives me the output X. So this is like the matrix multiplication thing. Okay, so think of an L network as matrix multiplication, and the weights are just the factors of the matrix. And X, which is the output of the network, is the result of the multiplication. So there might be many weights that generate that same output. Among all possible weights that generate that output, choose one that minimizes the sum of products of weights. Sum from 1 to the number of parallel subnetworks. Here it was sum from 1 to the number of factors. Okay. Before, that returned a function of X that was a norm. Now this still returns some function of X, which I don't know what it is. Okay? The key proposition is that that function is a convex function of X. Okay? And because it is a convex function of X, this thing that I talked about for matrix factorization, that there is a relationship between a convex and a non-convex problem, can still be made. So even though the neural network training problem is non-convex, there is a convex relaxation of it with this omega function, which is exactly defined in here. So here is the theorem now stated for neural networks. This is the training problem for neural networks. I minimize the loss plus the regularizer. There is an equivalent convex problem at the output of the neural network that says, given the labels, compare it with the outputs, plus a super fancy, complex, and maybe ununderstandable regularizer on the output of the network. But even though I don't know what it is, and it may be complex, it's convex. And so this associated problem here is a convex problem. Okay, so I've got non-convex and I got convex. What is the theorem? The theorem says, if you find a local minimum of the non-convex such that all of the weights of one parallel subnetwork are 0, that local minimum is a global minimum. Moreover, phi of those weights, namely the output associated with those weights, is also a global minimum of this convex problem in here. Okay. And the second theorem is essentially the same that I mentioned for matrix factorization, which is that if the number of parallel subnetworks is large enough, then this meta-algorithm is guaranteed to find the global optimum network. And the way it does it is as follows. Start with your stochastic gradient descent or your favorite method, you go down. This is for a fixed network size. If you are at local minimum, check, are the weights 0 for some subnetwork, yes or no? If no, then you add a parallel subnetwork and you optimize again, and that will eventually get you to the global minimizer. Okay? So I don't have experiments, but Raja will have experiments, and so I'm actually copying here Raja's experiments, where he used this type of regularizers for variants of AlexNet type networks, where he compared, for example, this is on the MNIST data set, What is the performance of doing no regularization? What is the performance of doing weight decay? And what is the performance of using these products of norms style regularizers? In his case, he's got something called a Jacobian, but it's very intimately connected to this product of norms, as he will explain in the talk. And so the idea is that the difference between no regularization and weight decay is relatively small. You do a little bit better. But there is a clear difference by using this regularizer. So in a sense, and the theory is not fully complete yet, but the hope, and I hope that in 5 years from now, we will have theorems that say you can find the global minimum using these regularizers, and these regularizers also generalize well. And now the things are sort of starting to converge because regularization is coming from one side saying if you have products of weights, that's good. The talk that I just gave is if you have products of weights, you can find global minimum. All right. So the summary is for optimization. Number one, size matters. The second message is that regularization matters, namely, you have to use regularizers of the same degree as the network. A network with 150 layers should have a regularizer of degree 150. Okay? And products of weights is one way to do it. The third message is that this is just the tip of the iceberg. We are very constrained in these results to networks where size is just one number. So number of neurons of a network with a single hidden layer, that's the one number. Or number of parallel subnetworks, that's the one number. But we'd like to have these results for number of neurons and for depth also, not just for width, which is the current results. The other aspect that needs to be improved is the computational aspect. This is all analysis, what the local minimum look like, but computing and avoiding the fact that some calculations are NP hard, it's still an open issue. So thank you for your attention.
Okay, so good afternoon or good morning, everyone, depending on what hour did you wake up. So, so continuing after what René talked about, so the first part that René talked about was about optimization in deep learning. And I will talk about another aspect, or about two aspects. Now I will talk about generalization error, and after the break I will return to talk about optimization with deep learning, but from a different perspective. So just a short scheme, if you miss it, probably not. So deep learning is giving excellent results in many, many domains. We got some nice results also with deep learning. And the message that I will try to convey in my part of the tutorial is that if you want to get better results in deep learning, you should understand better why it is working, and this is the main scope of this tutorial. And one specific aspect that I think we are missing when we deal with deep learning is that we are focusing very much attention on the structure of the network, but we forget to take care or to take into account also the structure of the data. So here you have an example of a denoising work that we did, and we find out that if we train a denoiser not just for all the images in the world, but just for one specific class of images, we get much better results than an agnostic denoiser. So you can see here that if we make denoising just for faces, we get much better way the details of the hair or the eye than compared to an agnostic denoiser. And this is very useful because all of us are taking selfies, and when we take selfie, we don't care about the background, we care about ourselves. So, and also when you take care about the data, so you can also design better depth cameras. So this is a work that we design depth camera with just one lens, where we change the optics such that we get better results with one lens and modified optics compared to regular monocular depth estimation or compared to light row. So these are the light row results, these are our results, and these are the depth results that you will get for these scenes if you will use standard network that just look at the RGB. So I will return to the notation. So the goal of this tutorial, as René mentioned, is to try to understand why deep learning works, so we are not there yet, but we will try to get a bit more insight into the deep learning. So basically, deep learning is concatenation of this basic block where we have a linear operation followed by a nonlinear operation. And then if we concatenate these blocks, we get a neural network. And if you concatenate a lot of blocks, you get deep neural network. So, and of course, if you add skip connection here, so you get ResNet. If you add feedback, you get recurrent neural network. But this is the basic structure of a neural network. And if we replace the linear operation by convolution, we get convolutional neural network. And for the nonlinear part in the network, we have three general nonlinearities. As René mentioned, we have the ReLU, which is the maximum between the input and zero, the sigmoid, the hyperbolic tangent, and we have also different type of pooling operations. Now, when we try to understand why deep neural network works, there are lots of interesting questions, like what is so special with the structure, what is the capability, how many training examples we need, and so on and so forth. So when René talked, he focused on the optimization perspective and when we can claim that a neural network reached the global minimum. But when you train a neural network, you have two important things in the optimization to take into account. One of them is the question of whether you go to the global minima or to a local minima, which René talked about. The other one is whether the global minima that you achieved is good only for the training examples that you get, or does it generalize well to new examples that you don't have. And I will focus on this specific aspect now. So I will use this view of a neural network that I believe is helpful to understand its functioning. We will assume that we have just two classes. We have the blue class and we have the red class here. And a neural network transforms these classes from their input domain to some feature domain. And and in the feature domain, the network is applying a linear classifier or softmax, and in the case that you have two classes, softmax essentially can be viewed also as a linear classifier. And hopefully what you want to achieve is that after you transform the input data, the data from its input domain to the feature domain, the data will be linearly separable. Now, the separating line that you get in the feature space corresponds to a separating boundary which is nonlinear in the input space. So basically, when you are training a neural network for classification, I think this view can be very helpful to understand what's going on. You are taking data from the input space, you transfer it to a certain feature space. In the feature space, you separate it by a linear classifier or by a simple classifier, and this simple decision boundary that you have in the feature space translate to a nonlinear decision boundary in the input space. Now, the important question is what we can say about the classification error that we get if we get a new example. And this brings us to the question of the generalization error. So when you train a network, you reduce the classification error, L training, of the training data, as the number of training examples increases. However, we are interested not in reducing the classification error of the training data, but in reducing the error in the test data, or in data that was not seen before. Because obviously, if your task was just to classify the training data, you don't need to do anything. You already have the labels. So just use one nearest neighbor classifier. Now, in René's talk, his focus was how we can achieve the global minima with the training data. An important question is what we can say about the difference between the error in the training data and the error in the test data, and this is called the generalization error. Now, I know this is not the formal definition of generalization error. The formal definition of generalization error is the difference between the expected loss and the empirical loss. And in our case, the expected loss is the error of the test data, which approximate the expected loss, and the empirical loss is the loss of the training data. So we are interested in minimizing the generalization error. And it is very important to understand the generalization error of neural network, but you should remember that when you want to understand the functioning, you cannot focus only at the optimization or only at the generalization error. Because if you focus just on the optimization, which is the first part of the tutorial, you may get great global minima, but you will get to overfitting. On the other hand, you can use a random classifier, which has the same functioning on the training data and the test data, and it gets 0 generalization error, but I assume that you know that random classifier is not a good thing. So we care about both terms, both the generalization error and the optimization. So because René already surveyed the optimization, I am left with the generalization error. Hope you will enjoy it. So one of the first bounds that were derived for the estimation error of neural network was derived by Baron in '94, and sometimes we forget that neural networks were before 2012. So there were great results before that. So he showed that the bound on the estimation error of the network is composed of these two terms. The first term bounds the approximation error on the training data, and it scales as the smoothness of the approximated function divided by the number of neurons in the network. And in this bound, you can see that the more neurons in the network you have, the better approximation you can get for the training data. So this is the error on the training data. And then he has another term, which is the generalization error, and in this term, you can see that the generalization error increases when the number of neurons increase, because then you can more easily overfit. But on the other hand, the generalization error is decreased when the number of training examples increases. So this is one of the first bounds that studied the trade-off between the approximation error and the generalization error. In this talk, I will focus just on this part. And there are many works that try to reduce the generalization error by adding regularization. So there are many regularization techniques, such as weight decay that René mentioned. We have dropout that randomly drop units from the network, or drop connect that extend dropout. We have batch normalization that try to whiten the data to reduce the generalization error. And we have also stochastic gradient descent, which initially people were using because of because it is more computationally feasible, but it has been recently shown that stochastic gradient descent is not just a good computational tool, but it also provides a good generalization. Or it can be shown that stochastic gradient descent can be viewed as a kind of regularizer for the network. And there is the PassSGD that try to balance the weights in the network, and there are many other regularization techniques. Now I will take a sample of two recent generalization error bounds. One of them is based on the VC dimension, and it has been recently shown that the VC dimension of the network with ReLU is of the order of the number of parameters in the networks time the depth of the network, and it has been showed, I think, by Bartlett recently, that this is a very tight bound. And Shalev Schwartz and Ben David showed that the generalization examples divided by the number of training examples. Now, in this bound, we have two important factors. First of them is that the generalization error reduces when you add more training examples, which is something that we would expect. So anytime you see a new generalization error bound, you should always look for this 1 over square root L term that tell you that the error, the generalization in the network reduces as a factor of square root L. On the other hand, in this bound, we see that as in Baron's bound, the generalization error increases with the number of parameters in the network. Now, from practice, we know that sometimes if you widen a network, as happened with the wide ResNets, the generalization error doesn't become worse than if you use other networks with less parameters. So for this reason, Bartlett in '98 and then Neishabur in 2015 showed that if you put a constraint on the Frobenius norm of the weights in the network, then the generalization error that you can get generalization error bound using tools from the Rademacher complexity that is independent of the width of the network. So you can have layers that are very wide, but if the norm of each layer is bounded, then the generalization error is not affected by the number of neurons that you have in each layer. On the other hand, the bound by Neishabur added exponential complexity on the depth of the network. So, and again, in the bound by Neishabur, you have the 1 over square root L, which claim that the generalization error reduces as the number of training examples increases. So, and now, so if you look at these two recent bounds, the bound by Shalev-Schwarz and bound by Neishabur, you can see that in both of them you have dependence either on the number of parameters in the network or exponential dependence by the depth of the network. And if you look at the ResNet with the 1,000 layers that was trained for CIFAR, so obviously this network generalized well, and it doesn't use 2 to the power of 1,000 training examples. I think it's more than the number of atoms that we have in the universe. So, and they generalize well. So, yeah.
The original bound that you showed depended also on the dimension of the input, but these two do not. Could you comment on what happened, why they didn't? Maybe repeat the question.
Okay, so the bound that we have here rely on the input dimension, but these two bounds are independent of the input dimension. Now, here, if you look at the bounds, the input dimension, so if you look at this network, so you will see that the size of the network is also dependent on the size of the input dimension. So therefore, it's hidden here somewhere. So the size of the network is hidden in the fact that the network swell as the input dimension. Okay. So you can see that both these generalization error bounds grows with the depth. And so we were not happy with this result, and we decided that we want to, because of practice, the networks that has lots of training examples generalize well, so we expect that we should have a generalization error bound that is independent of the number of parameters. Now, last year, or this year, paper came by Ben Recht and Sami Benjo, which is called the Rethinking Generalization, where they show that if you take, they looked at the CIFAR dataset, and then they trained lots of networks with lots of different regularization technique for the CIFAR dataset. One time they took the CIFAR dataset with this regular labels that the CIFAR dataset has, And one time they took the cipher dataset and gave it random labels. Interestingly, when they looked at the error in the training data, both with the true label, both in the case of the true labels and in the case of the random labels, the neural networks with all the regularization techniques got almost the same training error. However, when they looked at the test data, clearly the network on the true data generalized well, while the network on the test data, which has just random label, didn't generalize well. So their experiment suggests that if you want to understand the generalization error of the network, it is not sufficient just to take into account the network architecture. You must take into account also the structure of the input data. If your input data has structure, it means that the network will generalize better than the case where your input data is just random. And therefore, we should have generalization error bounds that depends not only on the network architecture, but also depends on the structure of the data. So we use the theory of the robustness framework by Xu and Manor. And we have the following bound, which claim that the generalization error is smaller or equal than the covering number of the data that we have, with balls of size gamma divided by 2. And I will explain a bit what is this covering number, divided by square root L. So let's leave this number for a moment and look at this bound. So in this bound, we have two terms. We have this term, and we have the 1 over square root L, which is the same thing that we had before, which showed that the more training examples we have, the better generalization error we get. Now, what is this term? So this term claims that the generalization error is depends on the complexity of the input. The covering number of the input is the number of balls with size gamma that are required to cover all the input data that we have. And what is gamma? Gamma is the input margin of the network. So what is the input margin? So if you remember at the beginning at the scheme that I showed, when you have a network for a certain data, so you have a decision boundary you have a certain decision boundary that is implied on the input data, and then you have a distance between each point in the training data and this decision boundary. So we look at all these distances. So these distances are called the input margin. And then our bound claim that the generalization error depends on the size of the covering with balls of the size of this input margin. So obviously, if you have bigger margin, you can use larger balls. And if you can use larger balls, then you need less balls to cover your data, and therefore your generalization error will become smaller. So essentially, our bound claim that the generalization error depends on the size of the input margin. Generalization error, either you increase the number of training examples or you increase your input margin. Now, the problem with increasing the input margin is that maximizing the input margin is as hard as training the network. So we try to solve a problem with more complicated problem. So instead of maximizing directly the input margin, we derive the lower bound for the input margin that depends on the output margin of the network, divided by certain terms that depends on the network itself. So let's look at the lower bounds that we got. So we have three lower bounds. One that depends on the Frobenius norms of the weights, one on the spectral norms, and one on the Jacobian. And the one on the Jacobian is the tightest one. So let's look at the terms. So in all terms, we have that the input margin is greater than the output margin divided by something. So basically, if we want to maximize the input margin, we can maximize its lower bound. So basically, we can maximize the output margin. And maximizing, unlike the input margin, maximizing the output margin is an easy problem. So if you look at SVM, SVM essentially maximize the output margin. So we can see here that if we maximize the output margin, we can get better generalization error, and this is something that is feasible. Now let's look at the denominator in the lower bounds. So let's focus now on the weakest lower bound that we have. We have here that we can see here that the input margin is greater or equal to the output margin divided by the product of the Frobenius weights, of the Frobenius norm of the network. And basically it means that if we want to have big input margin, we should bound the weights of the network. And bounding the weights of the network is done by weight decay, but notice that here we need to minimize the product of the Frobenius norm of the weights and not the sum of Frobenius norm of the weights. And as you have seen in the talk of René, also in his talk, he got that a better way for regularization is to use the product of the Frobenius norms rather than the sum of the Frobenius norms. And it's interesting that we get this result both, we get that this is better both from the optimization perspective and from the generalization error perspective. So from two different perspectives, we get to the same conclusion. Now we look at the tighter bound that we have. So we get that a better bound than minimizing the Frobenius norms is minimizing the spectral norm, and this is related to what is done in weight normalization or in other regularization techniques such as batch normalization. Because of time, I will not go into that, but the details are in the paper. So our bound also draw relationships to why batch normalization give better generalization error. But I will go to the tightest bound that we got, and the tightest bound relates the input margin to the norm of the Jacobian of the networks. And the Jacobian of the network is, if you use ReLU and max pooling, it is a piecewise constant function, and therefore it is easy to calculate it. And we can see that using the Jacobian of the deep neural network lead to a better bound. So if the Jacobian, if minimizing the Jacobian lead to a better bound, so we thought that we can use it also in practice. So as René mentioned, we compared network with no regularization, network with regularization of weight decay, and network with regularization that depends on minimizing the Jacobian of the network. And interestingly, we got better results when we use the Jacobian regularization compared to the case where we use the standard weight decay. So this is just one experiment. In the paper, we made much more experiments and combined the Jacobian regularization with batch normalization and with many other regularization techniques. And we showed that always using this Jacobian regularization instead of the weight decay give you better generalization error. And the nice thing is that we started from theory for bounding the generalization error. And this theory led us to new, better regularization techniques. And therefore, I think that if we want to improve the practice of deep learning, so trying lots of architectures and trying to get the best result in the ImageNet is a nice way to do that. But an alternative way is to try to derive bounds and then get better understanding of the network. And maybe this will lead us to better tools to use these networks to lots of new applications. We also extended our theory to the case of when we have invariance in the data. So one of the reasons that convolutional networks are used for images, because we know that convolutions are shift invariant, and therefore they get better performance than fully connected layers. So we thought that maybe we can formalize it. So we studied the generalization error of invariant networks compared to the generalization error of non-invariant networks. And we showed in a recent paper that if you take a network which is invariant to T transformations, then you can show that the generalization error of the invariant network is better than the generalization error of the non-invariant network by a factor of 1 of square root of T. So adding invariance to the network can give you better results. And then this theory also led us to another new regularization technique where if we want to impose invariance in the network, so we take our data and apply the different transformation that we want our data to be invariant to, and we require the features in the network at the last layer to be the same after applying the different transformations. And in this way, we force the network to be invariant. And we got that this new way to impose invariance give better performance compared to the case where we don't use regularization. And we also combined our new way to impose invariance with another recent paper that averaged the representations. And our combined way to impose invariance gave the best results compared to using each one of them alone. So I will stop now because I believe all of you want to drink coffee or tea. And we will continue after the break at 11 o'clock. Thank you very much. Welcome back to the tutorial on the mathematics of deep learning. In the first part of the tutorial, René gave us a survey of open problems in theory of deep learning. Then he discussed conditions when local optimum of the optimization in neural networks achieved the global minima. Then I discussed the generalization error in neural networks. And now I will talk about, I will return to the issue of optimization in neural network. And I will discuss how neural network may solve optimization problems. So I just want to mention that all the slides of this tutorial will appear on the website of the tutorial. If you will go to the tutorial page and we will click on the tutorial link, you will get to a web page where you will be able to find all the slides. And if you don't find them there, so they're also available on my website. So if I didn't say, so my name is Raja Jirias. I am from Tel Aviv University. And I think they're also available on René's website, and I think also on Verdun's website. So in this part, I will focus on inverse problems. So inverse problems are important problems. They appear on all sorts of applications in denoising, the blurring, super resolution. And essentially, if we will consider for simplicity the case of linear inverse problems, then you will have that in inverse problems, you have that you have set of measurements V, which equal an unknown signal Z times a measurement matrix A plus noise. And we want to recover the unknown signal Z from the measurements V. So Z can be the high resolution image and V is the low resolution image. Z can be the sharp image and A can be a blur operation and V can be the blurry image, and so on and so forth. Standard technique for recovery of Z from V is minimizing this optimization problem. You want to find the vector Z that obey the measurement model, in the sense that if you multiply Z by the measurement matrix A, and subtract V, you will get a term that is as small as possible, such that Z belong to some set, which we assume to be low dimensional. So we have the measurements term, and we have the data term. And essentially, all solvers of inverse problems are of this sort, where you have a measurement terms and some assumption on the structure of the data. And you have the unconstrained form of this minimization problem, where you minimize the distance between your Z times A and the measurements, and you have some regularization term, which penalize Zs that are far from the model. And in this term, we have lots of minimization problems that are known to the most of us. So F can be the L1 norm, and then it imposes some sparsity on Z, or F can be the total variation norm, and then we have here the total variation denoising, or any other penalty function that you may think of. Now, I will focus on the L1 minimization case. If we try to minimize this problem, try to find Z, which has a small L1 norm, such that Z times A is close to V. So this is a context problem. Yet, if you go to high dimensions, trying to solve it directly using interior points methods or other solvers, it's very hard. So one efficient way to solve this problem is using the iterative shrinkage and thresholding technique known as ISTA, where in this technique you perform two steps. The first step, take a gradient step with respect just to the measurements term. So here in the parentheses, you have basically a gradient step that in the direction of minimizing the least squares here. And after you take the gradient step, you apply a proximal mapping, which is related to the L1 norm that you have here. And the proximal mapping is an element-wise operation that look at each entry here in the outcome of this gradient step and perform the following element-wise, entry-wise operation. It takes each entry here and apply what is called soft thresholding or shrinkage. It takes each value. If the value here in the parentheses, if the entry is smaller than lambda mu, here lambda is the regularization term here and mu is the step size. So if the value is smaller than lambda mu in the absolute value, you reduce lambda mu in absolute value. If the term you have here is smaller than lambda mu in absolute value, you just zero the term. So you apply this very simple nonlinearity, which is very easy to apply. It's just element-wise and very easy. And then you get your new estimate for the solution of this minimization problem. Then again, you apply a gradient step, which involves just applying A and its transpose, and that's it. Followed by another simple nonlinearity, you get the next estimate for this minimization problem, and you iterate. So the advantage of the ISTA iteration is that it is very efficient to apply. You just need to apply the linear operation and its transpose. So in many cases, so if your linear operation is, so you don't need to apply inversions or things like that. So if A is convolution, is a convolution kernel, like in the blurring case, so you just need to apply convolutions. You don't need to store the convolution kernel in memory or can you hear me in the back? No. Can you hear me? Okay. Someone want to hide this information from you. Okay. Oh, hello? Hello? Okay. So the good guys win. Yeah. So basically, if A is the Fourier transform, so you don't need to store it in memory. So it is very efficient. You just need to apply A and A transpose and a simple element-wise operation. And then the problem yet with ISTA is that you need hundreds of iterations for it to converge. And in many applications, you don't want just good solution, you want to get it fast because of some time constraints. You want to have real-time performance. So many acceleration techniques were proposed for ISTA. I think most notably is the FISTA algorithm, which is fast ISTA. But I will focus, because now we're in the tutorial about mathematics of deep learning, I will talk about the neural network-based approach to accelerate the ISTA convergence. So what is the LISTA approach? So you take the ISTA iteration, and then you reorder the terms such that if you look at these terms, I just reorder them, and then take the linear operation that multiply my previous estimate of Z, and the linear operations that multiply my measurements, I reorder them, and then instead of this linear operation, I replace this linear operation with X, and I replace this linear operation with S, and I get here new linear operations, and what I do is the following. I train the linear operation X and S such that after 10 iterations of LISTA, I will get the same result that I get with ISTA after 1,000 iterations. So I take lots of data. So let's assume that I want to apply ISTA for images. So I take lots of patches from images, apply to all these patches ISTA for 1,000 iterations. I store the patches and their ISTA solution. And then I train the matrices X and S such that if I apply this operation for 10 iterations, I will get result which is as close as possible to the result that I get with LISTA. Alternatively, if I have ground truth, if I have the true Z, and I can train LISTA to give me the true Z instead of the solution of ISTA itself after 10 iterations. And interestingly, so this approach was proposed by Gregor and LeCun in 2010. And interestingly, if you train LISTA on some training example and then apply it to new test examples that the LISTA network didn't see before, you get much faster convergence than the ISTA. And if you train the LISTA on the true data and not on the output of LISTA, sometimes you even get better error with LISTA within 20 iterations compared to the error that you get with ISTA. So here we have such a case where we train the LISTA network to approximate the true unknown signal Z using training data. And we got better lower minima than the ISTA one after 20 iterations. Yes?
Why the starting point is different?
Why the starting? Okay, so this is iteration 1. This is not iteration 0. So this, even after 1 iteration, you get much better. Now, this graph to be, okay, so this is not the LISTA iteration. This is, I trained here LISTA with 1 layer. This is LISTA with 2 layers. So these are different LISTAs. So I just show that if you pick one with 20, you will get here. You train one with 1, you get here. But if I will draw the one with the 20, it will have a smoother curve. But in any case, you have this LISTA magic that you take an algorithm which has guarantees for convergence, very specific structure for the linear operations that you apply in it. You replace it with learned operations that you just learned. You have no idea why these are the learned operations. And you put new data and you get faster convergence and it works. And you're happy, but you don't know why. Now, if this was the case only for L1 minimization, we would say, okay, so maybe this is something special for L1, but series of works, like the work by Sprechman, Bronstein, Sapiro, they show that you can apply Lista not just for the standard sparsity with L1, but so in this experiment that I show here, so Z is sparse. So it's very sparse, and we use L1. So they applied it also to low-rank matrices, and the analysis called Sparse model. In a work by Renes, Litani, and Bronstein, they applied the Lista idea to nonlinear inverse problems where you have a quantization to just one bit. And they got also faster convergence than just using iterative methods. So, and then there is the work by Thompson, Schlatter, Sprechman, and Perlin that applied the Lista idea to the Eulerian flow simulation. And this idea of taking an iterative algorithm, taking its linear operation and replacing it with a learned operation, learning it and getting better performance than the original algorithm which has proven convergence applies to many, many problems. The group of Thomas Pock has also lots of works in this respect where they take variational methods and replace the standard parameters that have some just mathematical justification before them and just learn the operations, get faster convergence, get better results, and you're happy, but till recently we have no idea why. Yeah.
Can you comment on why can't I push it to the limits? Instead of training the network to learn the result of 20 iterations ahead, be faster, just training to give you the minimum. So what is some trade-off on maybe to get to 20 iterations and in a bigger network or something?
So if I understand the question correctly, so there are two approaches. So the idea in Lista in general is that you assume first that you have a certain budget of certain number of iterations, and then you try to get the best that you can with this budget. Now, there are two approaches for training a network with this budget. One of them is taking the standard iterative approach that you know to be it converge, and train the new network with the 20 iterations to get the same performance like the iterative method with the thousands of iterations. Another approach is to forget about the iterative problem that you know and try to minimize with the 20 iterations the original objective that you have. And the work of Sprechman, Bronstein, and Sapiro suggests this, this strategy, and they show that in many cases it converges much faster and gets to better results. So many times it's better to tackle directly the initial objective instead of the approximation of certain minimization algorithm. And in other cases, like what the group of Thomas Pock is doing, you can take the original data. So if you have the blurring case, so you take the blurred data or noisy data and the clean data, and you try to reconstruct the original signal. So you can use whatever objective you want. But amazingly, it works. And so we will try to gain a bit of understanding why it works. And I will provide one possible explanation for the success of this trick, that you take an iterative algorithm, you unfold it, train the weights, and get better results. And then I will mention other parallel works that give other aspects to this explanation, and I believe that all of them give us better understanding. So if you look at the Lista iteration, you can view the Lista iteration as a neural network. You have the input, you multiply it by a linear operation, apply nonlinearity. So in the case of L1 minimization, it is the shrinkage, which basically, if you will think about if you will think about the soft thresholding, shrinkage, and the ReLU is just one-sided soft thresholding. And I believe Vardan will elaborate on it more. So you take the linear operation, multiply it by the input, apply a nonlinear operation, and then you have an estimate, but you take this estimate, multiply it by another linear operation, add it to the previous solution that you have, apply another nonlinearity, and continue. And this structure is quite similar to what you have in RNNs. It's slightly different, but you have here a structure of, you may say, a recurrent neural network. Slight differences, but so Lista is a type of a neural network, and by learning it, we can solve optimization problems. And I think that understanding of why it is possible to solve problems with this type of structure of a network may lead us to a better understanding in general of why we can solve with general neural networks optimization problems, because at the end of the day, always we are trying to solve a certain optimization problem. So if you remember from the talk of René, he showed that you can relate the solution, you can relate the optimization of the neural networks of the structure that he was looking at to another optimization problem that he showed to be convex. So in some sense, if we can relate the structures of neural networks to certain optimization problems that we're trying to solve, we will be able to get better insight onto what really we are doing with the networks. And if we'll get better insight on what we are really doing with the network, maybe we'll be able to design them in a better way. And I will give you an example how we can do that. So this is the Lista structure. So we have the linear operation, we have to learn linear operation, we have the nonlinear operation, and so on and so forth. There is a small detail that I omitted. In Lista, you learn both the linear operations and also the thresholds. So if you remember, in ISTA, you have the threshold value in the soft thresholding. So here you also learn the threshold location for each entry. Now, if you look at this structure and replace these learned operations with some known operations, we get lots of algorithms that we are familiar with from other works. So if we have here the mu A transpose and the I minus mu A transpose, and here we have the hard thresholding, which just keep the largest k entries from the input. So this type of network, which has fixed linear operations, is the iterative hard thresholding algorithm, which is very popular in sparse recovery or sparse coding. And it basically solves, aims at solving the constrained sparse recovery problem. If we replace the hard thresholding with projection onto the L1 ball, then we get a solution to the constrained L1 minimization problem. And projection onto the L1 ball can be done efficiently, and it results also with a soft thresholding operation, but instead of soft thresholding operation with fixed value, the value depends on the input. And if we have here soft thresholding with fixed thresholds, so this network minimizes the unconstrained version of the L1 minimization. So if we have here soft thresholding with thresholds that depends on the input, we have this network estimates the constrained version of the L1 minimization. If the thresholds varies, if the thresholds are constant, then these networks basically minimize the constrained version of the L1 minimization. And to remind you, if we learn the linear operations by Lista, we get much better convergence. And we want to understand why this happens. So I will focus now on one structure of this network that is related to the projected gradient descent algorithm. The projected gradient descent algorithm is the general version of the network that we saw that solve the constrained sparsity problem or the constrained L1 minimization. So ISTA, in the nonlinear part, we have soft thresholding with fixed threshold. We will assume here that we have the same nonlinear linear operation that we have here, but in the nonlinear part, we'll assume that we have projection onto a certain set. Now, projection onto a certain set, including it the case of projection onto the L1 ball, it including it projection onto the largest scale, to the sparse set, but it doesn't include the case of ISTA where you have here proximal mapping. But as I will show in a minute, we can also learn the linear operations here and get faster convergence. So we will analyze why it is possible to accelerate the solution of this type of problems. And I believe that by explaining how it is possible to accelerate this type of networks where we have here projection, it will give us also insights into why it is possible to accelerate the convergence of ISTA-type networks. So we'll analyze this part, this type of network. Okay. So in 2016, Oimak, Recht, and Soltanol-Kotabi came with the following theoretical analysis of the convergence of the PGD. They showed that if we work with the measurement model that I mentioned, then in the noise, they have a result for the they have a result for the general case where we have noise in the system. For simplicity, I will describe just the noiseless case. And they showed that at the tth iteration of PGD, the error scales as kappa f rho to the power of t times the norm of the original vector. So if we will look at this result, we will understand that the convergence of the PGD scales as this term rho, and we need to understand what is this term rho. So this term rho is the supermum of U and W over U and W that belong to the tangent cone that is related to F of U I minus mu A transpose WT. So instead of trying to understand what this term means, I will go to a relationship that they drew before this term rho and what is called the Gaussian mean width. They showed that the convergence rate Gaussian mean width divided by the number of measurements plus the signal dimension, or the Gaussian mean width divided by square root m, depending on the step size that you're using. But essentially, what their results show is that the more measurements that you have, they show that the convergence rate depends on two terms. One term is the number of measurements that you have. The other term is the Gaussian mean width of the set, which is related to the set that you are making the projection onto. So in order to get better convergence, you need to do one of the following. Either increase the number of measurements that you have, or decrease the Gaussian mean width. Now, in most of the problems that we deal with, we cannot control the number of measurements that we have because they are given in the system. So the way to accelerate convergence is to get better understanding of the Gaussian mean width. The Gaussian mean width is a measure that of the complexity of the data that you are using. So if your input data is k-sparse,
the square of the Gaussian mean width is of the order of the sparsity log the ambient dimension of the data. If your data come from a GMM or from sparsity with T structure, then your square of the Gaussian mean width is of the order of K. Now, in many cases, the set you are making the projection onto is much larger than the real dimension of the data that you are using. But the reason that you are making the projection onto the bigger set and not onto the smaller set that really describes the data is that making the projection onto the bigger set is computationally feasible, yet making the projection onto the smaller set is something that is computationally not feasible. And therefore, you compromise with making a projection onto the more complex set because you can do that. And therefore, you get slower convergence than the case when you make the projection onto the smaller set. So we suggest the following idea, which at the first glance can be trivial. We will get faster convergence by projecting onto the smaller set. And I will say, okay, you could do that from the beginning, so what is new with this idea? So the new thing that we come with, we say, okay, we don't want to project exactly onto the smaller set. We will project approximately onto the smaller set. So if we project approximately onto the smaller set, we add some error to the system. So let's assume that we can use the simple projection that we have here onto the coarser set that lead to slower convergence. And we can use this projection and combine it with another linear projection P, which we call it which adds some inaccuracy to the system. And if we take our unknown signal and multiply it by P and project onto this bigger set and decrease it by Z, we get error which is only epsilon. Now, what we get from this P also, we get that P give us a projection onto a smaller set compared if we've combined with a projection onto epsilon compared to the case when we project only onto epsilon. So instead of projection onto this big set or this small set, we project in an inaccurate way onto this set. So we get in this way two things. On the one hand, we project onto smaller set. Because we project onto smaller set, we should get faster convergence. On the other hand, we add error to the system. So if we add error to the system, we will get an error in the reconstruction. And here, we have our exact PGD or inaccurate PGD, where it has the same structure as PGD, but has also these linear operations which add some inaccuracy to the system. And we have the following theorem for IPGD, which is very similar to the one of PGD, but it has two terms. It tells you that the convergence rate of the inaccurate or inexact PGD is of the order of rho p to the power of t, where rho p is related to the smaller set, plus a term that is related to epsilon, where epsilon is the error that you add. So let's compare it to what we got with PGD. So in PGD, we have rho to the power of t. In IPGD, in inaccurate PGD, we have the rho p to the power of t, where we assume that rho p is smaller than rho because we project onto a smaller set, plus an error that depends on epsilon. So if epsilon is negligible compared to rho p, then the convergence rate that we get will be of the order of rho p to the power of t. If we will use lots of iterations, rho to the power of t will become very small, and therefore epsilon will be more dominant. So we have here a trade-off. If we can use just one iteration, so our goal will be to try to reduce rho p as much as possible, and we can allow ourselves to have very large epsilon, because we have just one iteration. If we have lots of iterations, so rho p to the power of t will become smaller, and then epsilon will be more dominant, and therefore we cannot use a projection that are very inaccurate. So we have a trade-off between the inaccuracy that we add to the system and the faster convergence that we get by it. And so I will demonstrate it with an example. Let's assume that you have a sparse vector that has tree structure. If you will think about natural signals have sparse representation in the wavelet domain. Now, if you will think, now the wavelet domain has tree structure. In the low frequency, you have very large magnitude. In the high frequencies, you have very small magnitude. So if you are allowed to use small number of iterations, what we can do, we can, in our reconstruction, just ignore the high frequencies. So if we ignore the high frequencies and project in our algorithm just onto the low frequencies, so we get an error epsilon, which is of the order of the magnitude of the elements in the system that correspond to the high frequencies that we have. So we constructed here a signal which is sparse such that in the low frequencies with the tree structure, such as in the lower leaves of the tree, it has smaller magnitude, and the higher leaves, higher level, it has higher magnitude. And then we compare it to the model-based compare sensing approach that was proposed by Brian Luke, where he proposed to use PGD with projection onto the tree structure directly. So we will see here the graphs of the convergence. So here in the blue line, you can see the convergence of PGD with just simple projection onto the sparse set. And then you can see here in the brown line, the convergence of PGD with projection onto the tree. So this is basically the best projection that you can do. Yet, this projection is computationally demanding. So we suggest to replace the projection onto the tree with just projection onto the certain levels of the tree. So here you can see the versions of inaccurate PGD with projection onto different levels of the tree, just on the first level, 2 levels, 3 levels, and 4 levels. Now, if you just project onto one level, you just get the DC. Of course, the error that you get in the signal is very large. So in this case, epsilon is much bigger than the gain that you get with the convergence. And then, because of that, the convergence that you get with IPGD with just projection onto one level is very bad. You can see that it gets very bad reconstruction error. But if you project onto 2 levels or 3 levels or 4 levels, you can see here in these lines that you get faster convergence at the first iterations. Now, as I mentioned before, the more iterations we go, the smaller the error that we want to have in the projection. So therefore, what we suggest is to use inaccurate PGD with changing levels. So at the first iterations, we want to get faster convergence, and we don't care about epsilon. So we project onto 2, 3 levels. Then after 3 iterations, we change it to projection onto 3 levels. Then after 3 iterations, we change it to projection onto 4 levels, till we get to projection onto the all sparse set, which is similar to the regular iterative art thresholding. And with this technique, you can see that we get faster convergence than the PGD with projection onto the sparse set in the first iterations in this violet line. And then afterwards, we got also faster convergence all the way. Now, I don't present it here, but if you will plot this same graph with respect to the computational time, you will see that our proposed algorithm gets faster convergence than the projection onto the tree, because we use simpler convergence. So this is the idea behind the inaccurate PGD, that you have a trade-off between the error that you add and the convergence speed. Now, we showed also relationship to spectral compare sensing. Now we get to the case where we don't know what is the projection P. So if we don't know what is the projection P, or don't have explicit information about the projection P, like in the case of tree structure, one way to solve this problem is to learn this projection P. So now instead of learning the projection P, we can learn, so in our algorithm, we have the I minus mu A transpose time P and mu A transpose P. Instead of learning the projection P, we can replace all these two matrices with two new learned matrices, and then we get the learned inaccurate PGD algorithm. And so our idea or our explanation for why it is possible to get acceleration using learning in iterative algorithms for solving inverse problems is that you can add inaccuracy to the projection when you have a limited budget of iteration, such that you project onto a smaller set and therefore get faster convergence with the limited number of iterations that you have. And also you can change the inaccuracy throughout the iteration such that in the overall you get faster convergence. So we looked at the learned IPGD, where you have where we replaced the linear parts in it with learned linear parts, and we learned them. So we looked at the case of super resolution. So a popular super resolution technique uses a pairs of low resolution and high resolution dictionaries. This is work by Zayde et al. From 2012, where they train dictionary for the low resolution images, and then they use the representation of the low resolution patches to reconstruct the patches from the high resolution image. And in their algorithm, they use orthogonal matching pursuit with sparsity level 3. So what we did, we took the OMP with sparsity level 3 and replaced it with learned iterative PGD with just 3 layers. Now, the advantage that we can have with the learned IPGD is that we can aim at larger sparsity. So in our experiments, we aimed at sparsity 20, but we have just 3 iterations. So it has the same complexity like OMP. We have just 3 iterations. It is even more less computationally demanding than OMP, because in OMP you need also to invert the matrix. In the learned IPGD, you just need to apply 2 matrices and the hard thresholding. So we learned the LIPGD and replaced the OMP, and we get in the reconstruction performance, we got improvement in the super resolution performance with up to ½ dB improvement. So this result will be soon in the archive version of the paper. And okay, so as you can see, so what we have done, we considered the PGD algorithm, and we have shown that it is possible to replace its linear part, add an inaccurate projection to a linear part, and therefore have a trade-off between convergence and accuracy. And then we show that we can learn this projection to get faster convergence. Now, if you look at the learned IPGD algorithm and the LISTA algorithm, you will see that there is a great resemblance between the two. In the learned IPGD, we have projection here. In the LISTA, you have proximal mapping. So we think that our explanation that apply to the learned IPGD can explain also why LISTA can get better convergence, and which is that you have here also a trade-off between the inaccuracy that you add in the proximal mapping to the convergence speed that you get. Now, with this understanding, we suggest the LISTA mixture model, where if what LISTA is doing is trying to approximate a certain low-dimensional set, then what we can do, we can use several LISTA models that each will approximate part of the data in our low-dimensional model. So we train multiple LISTA networks that can run in parallel and therefore have the same latency like one LISTA model. And we compare ISTA with LISTA and the LISTA mixture model, and you can see that the LISTA mixture model gets a faster convergence compared to the LISTA. So if I will summarize, so our explanation for why it is possible to accelerate iterative algorithms with learning is that sometimes when you want to solve a problem, you don't care into getting to the best solution that you can get, because sometimes you may have noise in the system. So when you have noise in the system, anyway, you will not be able to get the original signal. So if you, anyway, you will not get the original signal, you can add a small error into your projection, and in this way, you will project onto a simpler set, and in this way, you will get faster convergence. Now, and our understanding led us to having the new learned IPGD algorithm and to the Lista mixture model that get faster convergence. And there are other parallel works that provide explanation for Lista. Bruna et al. Has a work that connects Lista and matrix factorization, and it shows there that the learning may give better preconditioning and therefore faster convergence. Xin et al. Showed the relationship to the restricted isometry property, but both of these two works focus mainly on the sparsity model, and our work applies to the general low-dimensional sets. And Borgending and Schnitter made a connection between approximate message passing and the Lista network, but also there it's also only for the sparsity case. So if I will summarize this part of the talk, so we have seen that at the first talk of the tutorial that we can show a relationship between solving general neural networks to a convex optimization problem. And in this part, we have seen that we can look at specific inverse problem, take a specific optimization problem that we have, and design a neural network which is tailored for this optimization problem that you have, and get faster convergence and better approximation. So I will end now, and yeah. Again? So this is the LIPGD. So you basically multiply by X, apply hard thresholding, multiply by S, sum, apply hard thresholding, multiply by S, apply hard thresholding. You do it 3 times. In OMP, you multiply by A transpose, you take the largest element, you apply the inverse, you apply by A transpose, apply the inverse, multiply by A transpose, apply the inverse. So it's same computational cost. So we have 3 iterations, they have 3 iterations. But we can, with 3 iterations, get larger sparsity, or we can get better performance compared to, yeah. So are there other questions? Okay. So thank you very much, and I will.
Okay, so we have a QA session at the end. So TL Vardan is getting his slides. So if you have any questions to me or to René about our talks, so please feel free to ask. And
No questions.
yeah.
We're not talking about training, global optimization for training. We are talking about generalization, error minimization, how to link these two. Because one is on the training stage, and you are talking about the testing stage. So how can these two work together and get an overall benefit, best benefit?
So that's an active area of research. Prior work that I mentioned in passing suggests that stochastic gradient descent generalizes well. And the reason they suggest so is because if you have an objective function that has many local minimizers, some of them will be flat valleys and some of them will be very sharp valleys. And if you have a sharp valley, then small perturbations will not generalize well. But if it is more flat, it will generalize better. So there's been work arguing that stochastic gradient descent is able, via the smoothing and the stochastic part of it, effectively it's equivalent to smoothing the objective, and therefore it's much more likely that it converges to wide valleys as opposed to very sharp ones. So that's one connection. The second one is the one that I mentioned and that I think both of us have mentioned, which is that the regularization that based on products of weights has guarantees of global optimality, as I presented in my talk, and has good generalization properties as he presented on the talk. Making that connection tighter, because the assumptions made by the theorems aren't identical, is area of future work. And the third, and this is something that I didn't have the time to touch upon, but we have done recent work that is in the archives where we demonstrate the following thing. For matrix factorization, if you do drop out, and you minimize the expected loss with respect to the variables you drop out, that is equivalent to minimizing a loss plus a regularizer. And the regularizer is exactly sum of products of norms. Therefore suggesting that a particular type of optimization methodology, such as dropout, is equivalent to explicit regularization with product of norms for which you have global optimality guarantees. That result is only for matrix factorization so far, so the extension to deep networks is pending work. But I think this is a very active area of work. Things are very interrelated, and I think things are getting closer to each other to have that unified theorem, which is what you're asking for.
Here or here? Maybe here. Hello, everyone. My name is Vardan Papian, and my topic for today is signal modeling from convolutional sparse coding to convolutional neural networks. This is a joint work with Jeremiah Sulam, Yaniv Romano, and Professor Miki Elad. So this lecture will have 3 parts. In the first part, I'll talk about sparse representation modeling, Sparseland, and the theoretical results that were developed for this model over the last 2 decades, perhaps. I'll then talk about a specific extension of this model, which is called convolutional sparse coding, which has been gaining much popularity in recent years. And then I'll show a model which is called multilayered convolutional sparse coding, which is something we proposed in a recent work, which is tightly connected to CNNs. And the main idea would be to show how you can start with sparsity-inspired models and through different extensions go all the way until state-of-the-art architectures in deep learning. And the reason why you want to do this is because you can then basically leverage all the research in sparse representation theory to explaining what CNNs are possibly doing. So let's begin with the first part, which is modeling. I kept saying model, model, model. So what is a model? So as you all know, we're surrounded by data. So we have images, videos, text documents, etc. And one thing is in common to all of this data, the fact that it all has some internal structure in it. And if you would like to be successful in processing this data, you would like to first identify this structure. And the second thing you would like to do is then to leverage it to your advantage. Let me give you some example. Assume I give you some signal that was contaminated with some additive white Gaussian noise. And then I ask you, can you please denoise this signal? Can you give me the clean estimate? And what would be your answer? Participation. Please. So someone's drawing a piecewise linear signal for a good reason, but not really, because I didn't say that the true signal is assumed to be piecewise linear. So basically what I wanted you to say is that you cannot denoise the signal, because I'm just giving you information about the noise, not about the signal itself. If in addition I tell you that the signal is believed to be piecewise constant, then suddenly the guy who drew something like that with his hand is correct. So basically, then you can actually denoise this signal. So you can denoise once you have some proper modeling of the signal. So again, what is a model? A model is a mathematical description of some underlying signal of interest. It's almost like a religion, something you believe in about the signal of interest. And there were many, many different models developed over the years, starting from the original principal component analysis, which is super simple, to mixture of Gaussian models, which is basically a bunch of principal components. And then you have some other things such as total variation in more recent years. And there's always this sort of trade-off when you talk about models between how reliable they are to the data that you have, how well they can actually explain it, to how simple they are. And your model is always bound to be imperfect because you're trying to find something which is simple, and therefore it basically is not perfect to the data. So let me give you another example of a model. Another example is JPEG compression. So in JPEG compression, I give you an image, which is, for example, this one, and then I ask you, can you compress it somehow? So the way JPEG does it is by taking some non-overlapping patches from the image, and then applying on it some fixed transform, which is, for instance, the discrete cosine transform. So this is basically computing inner products between this neighborhood, this patch, and some predefined templates. And for each inner product, you obtain a coefficient, which is a single box in this. For instance, this is one coefficient, this is another, etc. Now, what JPEG believes in is that only this blue box should have dominant coefficients, and all the rest should be zeros. So this is the belief. And based on this, what JPEG manages to do is to replace, let's say, 8x8 neighborhood, which is 64 numbers, by a lot less numbers, because you now have to encode a lot less integers and doubles or whatever. Okay, so what am I going to talk about in this talk? I'm going to talk about data models, more models, except these ones, and their use. And almost any task in image processing and many tasks in machine learning rely on these models. Maybe not deep learning. And the specific model that I'll discuss today is called Sparseland. And I'll show again how you can start with this model and propose different variations and go all the way until deep learning. So, sparse modeling. The Sparseland model is tightly connected with different areas of research. And as a result, it has led to many state-of-the-art results in different applications. Now, going back to the example of image patches, this model takes an image patch and some dictionary. A dictionary is basically a collection of some prototype patches. And in this case, we have 256 of those prototypes, which are often called atoms. And again, back to what we believe in, this model believes that a patch is a linear combination of a few atoms taken from the dictionary. So basically here you can see that there are 3 different atoms which are multiplied by some coefficients, alpha 1, alpha 2, alpha 3, in order to form this patch. And there are 2 properties which are very important in this model. The first is redundancy and the second is sparsity. So redundancy because you replace an 8x8 pixel by 256 numbers, which correspond to the coefficients that multiply each atom, and sparsity because this is a sparse representation. Okay, so there's this analogy that you can do between Sparseland and chemistry, where you can say that the dictionary is in some sense analogous to a periodic table, and the patch here is in some sense analogous to a molecule that is composed of a few atoms from the periodic table. And you can also talk about this model formally. You can say that there is some sort of box which has a button that whenever you press, you obtain a random sparse vector. And this random sparse vector is multiplied by this dictionary to create a signal X. So basically, this means that this is a generative model because you know how data is born to this life. And there are certain fundamental questions in Sparseland, all of which were answered over the years. The most important, perhaps, is given a signal, how can you actually decompose it into the atoms that construct it? So, for instance, if I give you a dictionary with 2,000 atoms, which has and I give you a signal which is composed of a combination of 15 atoms, how can you actually find those 15 atoms? So the trivial thing to do would be just to go over the 2000 choose 15 possibilities, which would take a bunch of time, so it's impractical. So are we stuck? No, we're not. Because what you can actually do is first define the problem that you would like to solve, and then you can solve it using different approaches. So first, let's talk about exactly what would we like to solve. We would like to take a signal x and to find a representation alpha such that x equal to d alpha, and we would like also to impose the sparsity, which is here imposed using the L0 norm, which basically counts the number of non-zeros. And there's also this other variation of this problem, which basically says that x is not equal to d alpha, but it's only close to it, up to some epsilon. For instance, if you're dealing with some denoising problem, or because your model is imperfect and it cannot really satisfy this equality. Now, these problems are NP-hard, so just by defining exactly what we want, we haven't achieved anything. But there are two approaches for estimating their solutions. So the first approach is called relaxation methods, and the second is called greedy methods. So relaxation methods is basically connected to what Raja was talking about, and they say that you replace the L0 norm with some convex pleasant alternative, which is the L1 problem. And the second approach is greedy methods, which basically say don't go over all the possible places of non-zeros, which is 2000 choose 15, just choose this more wisely. So again, there are three options. There is the first option, which is basis pursuit, which says replace the L0 with the L1. And there are greedy approaches. So there is the matching pursuit algorithm, which takes the signal and computes correlation between this signal and some atoms in the dictionary, and then, for instance, picks the maximal one. Then you compute some residual and compute correlations again, and then you pick the next atom. So this is one sort of algorithms, matching pursuit, and a different sort of algorithms, which will play a very crucial role in this talk, is the thresholding algorithm, which is the silliest possible thing you could do. And this is actually what leads to state-of-the-art results in image recognition, apparently. What you do is you take a signal y, and you compute correlations between this signal and all the atoms in the dictionary. Basically, you compute d transpose y. And then, because you believe that the representation should be sparse, you just zero everything that is below a certain threshold. So if you're in this region, this means the coefficient is big, so you don't alter it. But if you're in this narrow band, then you just zero the coefficient. So this is basically promoting sparsity. And here's an example of why these things make sense. So you can, for instance, take a sparse vector depicted in red. You can create a signal and then try to infer the sparse vector by solving basis pursuit. Oh no. And then you can, it would be very funny if it restarts. And then you can just solve basis pursuit and obtain an estimated sparse vector. Voila, it actually succeeds. So the nice thing about sparse representation is that it's not just voila, it works. You can actually prove that it works. And you can prove when it works and why it works. So in order to do that, you need to actually characterize the dictionary. So one very simple characteristic of the dictionary is called the mutual coherence, which is defined as follows. You take the dictionary and you compute d transpose d, which is basically a bunch of correlations between different pairs of atoms. And then to compute the mutual coherence, you just take the largest off-diagonal entry in absolute value. And in what follows, I'll show all the theoretical results will rely on this quantity. Now, probably there are people here sitting which are familiar with sparse representation theory and think about other ways to characterize the dictionary, such as the RIP, ERC, Babel, Spark, etc. There are many. But for simplicity, I will focus on the mutual coherence. Okay, so again, why is this interesting? Why do you care about the mutual coherence? Because you can prove the following thing. You can prove that if you have a signal x, which has a sparse representation over a dictionary, which is then contaminated with some noise, and fed into a basis pursuit solver, then this alpha hat is guaranteed to be close to the original alpha. Why is this interesting? Because it means that you start with some clean signal x, you contaminate it with noise, obtain some alpha hat, and this alpha hat is close to the true alpha, meaning you can actually estimate the original signal by multiplying this alpha hat by the dictionary. And you can actually provide a theoretical guarantee that says that if the sparse vector alpha is sparse enough, where sparsity relies on the mutual coherence, then alpha hat is actually close to alpha. Okay. Now, several comments which might be important is that if the noise is 0, then alpha hat is equal to alpha. This is a worst case analysis, it's very crude. And also that you can provide similar guarantees for many, many other algorithms, including the simple thresholding. Okay, the second problem with sparseland is that I assume there is a certain magical dictionary which was given to me from above. And the question is, how do you actually get this dictionary? The answer is actually just learn it. So you take a bunch of data and you try to learn the dictionary that would best sparsely represent all of this data. And this is called in my language dictionary learning. But in this talk, I will not focus on the learning part. I'll just focus on the sparse coding part throughout the talk. Okay, the third problem with sparseland is why should you even use it? Is it good for, I don't know, images, audio, natural data of some sort? And there are two possible answers to this. One answer is that it has clear connections to other models that were developed over the years, which have proven to be successful, such as Gaussian mixture model. And the second is an empirical answer, basically saying that this model was used for many, many years, leading to state-of-the-art results in many applications. So basically, it has proven itself. So the difficulties of sparseland model have all been answered positively over the last 2 decades, I would say. Now, in my group, what we care about is actually image processing. We do a lot of image processing. And when you use the sparseland model for images, you immediately face a certain problem. The problem is that imagine you have an image of size 500 by 500. You would like to impose a certain model on this image. In our case, a sparse representation model. Now, the dictionary that you would have to use would be the size of the number of pixels of the image times the number of pixels times something. So let's say it's like 512 squared times 512 squares times some factor. So this is absolutely impossible to learn this huge matrix. And therefore, what people usually do is they work on patches taken from the image. So imagine you would like to, for instance, denoise an image. So what you do is you start with some noisy image. You extract all the overlapping patches. You apply the model, meaning that you denoise the patches using the sparseland model. And then you reconstruct the image somehow. Now, why am I talking about this? Because there is basically some underlying assumption in this way of processing data, which says that we believe every patch in the image has a sparse representation with respect to the same local dictionary in all spatial positions. And this brings us to the question, what is the corresponding model that is basically hiding behind the scenes? And this leads us to convolutional sparse coding, which is the next part. So convolutional sparse modeling assumes that, again, it's all about beliefs, religion, that a signal X is a summation of different local filters convolved with sparse feature maps. So basically, you have an image of a parrot, which has capital N pixels, and you assume that it's a summation of M different filters, which are of size N by N, convolved with these sparse feature maps. So these sparse feature maps basically answer two questions. They answer, the first question is, for instance, where does this filter appear at? It appears here, 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 etc. And the second question it answers is, what coefficient is this filter multiplied by? And this is basically encoded in the values in these locations. Now, you can also write this model in a mathematical way, so in a matrix form rather. You can say that the global signal X is a summation of different matrices Ci times vectors gamma I. So the idea is that instead of writing convolution between filter and a matrix, you can actually write this as a multiplication by some circular matrix, which is Ci. So Ci is a banded and circular matrix that contains a single atom with all of its shifts, and gamma are simply some coefficients ordered into a single vector. And you can actually write this equation in a more compact way as a multiplication of a single dictionary, which contains the different banded circular matrices, times a very, very long sparse vector, which basically contains all the different representations of all the filters. And you're starting to get probably by now some resemblance to CNNs because of this convolution structure. Stay with me and you'll see clearly the relation. So here's again the global dictionary, which is a concatenation of banded circular matrices, which you can also reorder and obtain that it's actually composed of shifts of this single local dictionary shifted in the different places. And why do we even care about convolutional sparse coding? So convolutional sparse coding is basically a special case of sparse representation model. Why should we care about this special case and not a different special case? Maybe I should impose a fractal structure on the dictionary. Maybe I should impose a random structure on the dictionary. So the reason we care about this model in particular is because if you look at the patch from the global signal and you look at the atoms that contribute to this patch, they're found in this small box which we call a striped dictionary. And the only coefficients that construct this patch are found in a striped vector. So basically the ith patch is a multiplication of a local dictionary times the local sparse vector. And if you look at the ith plus 1 patch, then you obtain the same thing. So basically you use the same striped dictionary times another sparse vector. So what you can see here is that every patch has a sparse representation with respect to the same local dictionary omega. And this brings us back to this underlying assumption that was employed for many years in image processing, where people assume that every patch in the image has a sparse representation with respect to the same dictionary. And this basically says that the model that was hiding behind the scenes was the convolutional sparse coding model. Okay, so I talked a little bit about theory of sparse representation. So you might want to check, can you apply this theory for this model as well, right? So imagine you solve this problem, which is written up there. And I told you that, assume you solve this problem using basis pursuit. So I told you that basis pursuit is guaranteed to succeed if the sparse representation is sparse enough, right? So it seems as if there is no problem. But if you plug, for instance, the following numbers, assume you have only 2 filters shifted in all the different places, which are of length, for instance, 64, then you can actually show using the well-known Welch bound from the 70s that the mutual coherence is lower bounded by this value, which means that your pursuit is guaranteed to succeed as long as the number of non-zeros is 4, which is ridiculous, because it means that you can only succeed once the global image is a superposition of 4 filters. So you cannot actually construct a parrot from 4 filters, which means that this is super pessimistic. And so the classic sparse representation theory does not explain why this model would be successful. And what we show in our work, one of them is that actually what you need to consider is not sparsity, but local sparsity. So going back to the global sparse vector, instead of assuming that the global sparse vector has at most 4 non-zeros, you want to consider local sparsity, which is defined using the following norm. The L0 infinity norm is defined to be the maximal number of non-zeros in a stripe taken from it. So basically you extract all the overlapping stripes from the global sparse vector and compute what is the number of non-zeros in the densest stripe. And then you can also define this problem that says I give you an image Y, and you're trying to construct it using a convolutional dictionary and a global sparse vector by also forcing this global sparse vector to be locally sparse. And again, the intuition behind this problem is very intuitive. Basically, you're saying that gamma should be L0 infinity sparse, which means that as a result, all the stripes are sparse, which means that all the patches have a sparse representation over the same dictionary omega. And once we've defined a norm, the L0 infinity norm, you might ask yourself, can we actually do something useful with this norm? Because I can define a bunch of norms, right? And what you can, for instance, you could ask, can you generalize the sparse representation theory to this new notion of local sparsity? And the answer is yes. You can show that if you have a signal Y, which is equal to some d gamma plus some noise E, where gamma is locally sparse, then this orthogonal matching pursuit, which is a special algorithm from the matching pursuit family, is guaranteed to basically succeed, to be stable. So you're guaranteed to find the correct support, which are the places of the non-zeros, and you're guaranteed to find a representation which is close to the true one. And basically what this means is that instead of having 4 non-zeros allowed globally, you can now allow the same, or actually not the same, but similar number of non-zeros per stripe. So the global number of non-zeros now scales with the dimension. And you can actually repeat the analysis for other sorts of sparse coding techniques. For instance, there is this lasso problem, which is written here. And there were many recent algorithms that were trying to minimize this problem using different approaches, usually ADMM sort of approaches in the Fourier domain. And actually, the work that I'm presenting later in the conference is also solving this problem. Now, the question is this problem guaranteed to be stable, to succeed, to do something useful? And the answer is yes. If you know that your underlying sparse representation is locally sparse, then you can show that this algorithm performs very well. And I don't go into details how well. And also you can see that you can actually set this Lagrangian parameter lambda, which is the trade-off of sparsity, analytically. Okay, so this is a tutorial on deep learning. So you're probably wondering by now, why am I here? The answer is because of the multilayered convolution sparse model. So there seems to be a relation between CSC and CNN. Both have the word convolution in them. Both have this convolution structure in their weight matrices or in the dictionary. Both are data-driven in the sense that they train from data that is given to them. And it is vaguely known that ReLU is a sparsifying operator based on some different works. And in what follows, what I'll show you is a principled way to tie, actually to analyze CNNs. But first, let's very briefly review CNNs. Although it was done already, I'll do it very quick. So CNNs take an input image Y and convolve it with a filter to create a response map, which then undergoes ReLU, which is a pointwise nonlinear function defined here. This threshold is actually the bias which is used in CNNs. You then do this again for another filter and another filter and another filter. And by now you have this three-dimensional volume. That's how people call it, which you then convolve with another filter, however, this time a three-dimensional one. This results in another response map, which also undergoes ReLU. And again, you repeat the process several times to create a bunch of feature maps. And this is only 2 layers of CNN, but in practice, people do this many times until a certain depth. And then you take the response, which is basically this thing, the three-dimensional volume, and you just feed it to a linear classifier, obtain state of the art, and become happy. Now, notice that the convolutions by a set of filters, as was already mentioned in this tutorial, can actually be represented as a multiplication by a matrix. So this brings us to a mathematical description of this algorithm, which is called the fourth pass of CNN, which says you take an input Y, which is, for instance, the image vectorized into a long vector, and then instead of, or convolving with a bunch of filters is actually, oh no, I knew this would happen. I blame Raja. Cancel? Thank God. Oh no. Oh no. Oh no. Oh no. Okay, I blame Raja. I don't think it's working. I think it's restarting. No, I think it's restarting. Okay. Oh. Oh no. Sparse modeling, convolutional sparse modeling, multilayered convolutional sparse modeling. So you think it's not restarting? Okay, so you take an input Y, and instead of convolving it by a bunch of, something is weird. instead of convolving it by a bunch of filters, you can actually just multiply by a matrix W1 transpose that contains the different filters in all the different positions. So this is equivalent to convolving in CNNs by a bunch of filters. Then you add some bias and apply ReLU. So this is the result of the first layer of CNN. And then you repeat this process. So you multiply by another set of filters, which is again a multiplication by a matrix W2 transpose. You add another bias, apply another ReLU, and this presentation is for some reason broken. Okay, and now I go back to the sparse representation, and I'll show how you can actually connect sparse representation to CNNs. So the convolutional sparse representation model believes that a signal X is a multiplication of some convolutional dictionary times a global sparse vector. And we propose to impose another structure on the representation themselves, that the representation themselves can be represented as a multiplication of another dictionary, D2, times another sparse vector, gamma 2. Again, all about belief. And the reason why you might want to do this is because, you know, you can train the convolutional sparse coding model. You can take these gammas and you can actually look at them and you can see there is certain structure. And you can actually leverage this structure by imposing some model assumptions on it, like we're doing here. And then we obtain the multi-layer convolutional sparse coding model. Now, the intuition behind this model is that X, let's say it's an image, D1 is a convolutional dictionary that contains, for instance, a bunch of wavelet filters in different orientations and different positions. And D2 would contain basically a bunch of, I would call them sparse coefficients. And imagine that you take the first column here and multiply it by D1, then you would obtain some effective filter, I would call it. And this effective filter would basically combine a few of these Gabor filters to create a higher level atom, which I would call a molecule. So again, there are certain coefficients here that linearly combine a few of these filters to create a higher level atom. And once you move, for instance, to D3, which is not plotted here, you would combine these higher level atoms to combine even more high level atoms. So you start with atoms, you combine these to create molecules, you combine these to create cells, and you go all the way to state of the art. And you need to remember that this sort of viewing the model is good for intuition maybe, but a key property that we assume is that always the intermediate representations are sparse as well. This is important for theory. Let me give you just a small example of how these dictionaries might actually look. And this is based on a recent work that you can actually find in my website. So there is the dictionary D1, which contains the different filters here, which are, as I said, Gabors in different shifts, approximately Gabors. Then you can look at D1 times D2, which is what I said, a superposition of certain Gabors that creates more sophisticated atoms like this, which is a part of an arc, or maybe this, which is like a T-junction sort of thing. And then you can look at D1 times D2 times D3, which already contains parts of digits, for example. Okay. Now, assume I give you these dictionaries, and I would like to find the representations over the different layers. So we define the deep coding problem, which basically takes a signal X and tries to find the representation gamma 1 such that X equal to D1 gamma 1, where gamma 1 is sparse. Then gamma 1 should be equal to D2 times gamma 2, where gamma 2 is sparse, all the way until the deepest layer. And you can also define what is called essentially a projection problem, where instead of forcing equalities, you relax some of the equalities to inequalities. So assume I give you a signal Y, and you would like to find a signal which is actually in the model. So you solve Y should be close to D1 gamma 1 up to some epsilon, and the rest of the layers should be equalities. And again, going back to that recent work that I mentioned, you can actually do this and show, for instance, you take a signal Y, which is an actual digit from MNIST, and you can project this signal onto the model. So you can show the model is non-empty, it's interesting, etc. So you can actually obtain a signal X, which is equal to D1 times gamma 1, where gamma 1 is very sparse. Gamma 1 is D2 times gamma 2, where gamma 2 is sparse, all the way until the deepest layer. Okay, so I defined the problem, which is the deep coding problem, and I would like to somehow solve it or estimate its solution. And the way I'm going to do it is using the simplest, silliest algorithm known to sparse representation field, which is the thresholding algorithm. So we take y equal to d gamma plus e, where gamma is sparse, and we estimate gamma by applying the thresholding algorithm. So again, we take y, we correlate it with a bunch of atoms in D, and then we apply some thresholding operator. So for instance, you could apply the hard thresholding, which Raja mentioned, you could apply the soft thresholding, which Raja mentioned, and you can apply the soft non-negative thresholding, which is basically a soft thresholding that assumes that the underlying coefficients are non-negative. And in all cases, you basically impose or promote rather sparsity because you cut off everything which is below a certain threshold. Now, you're probably noticing that this soft non-negative thresholding is nothing but a ReLU with a certain bias. Okay, so let's put the pieces together now. So here's the problem that we would like to solve or to estimate its solution. And I was saying that we're going to do it in the silliest possible way. So imagine the layered thresholding algorithm. It takes a signal y and estimates gamma 1 by using the thresholding algorithm. Then given the estimated gamma 1, it estimates gamma 2 by using another thresholding algorithm. And then you obtain a formula which is very reminiscent to what the forward pass of CNN is doing. Because in both cases, you take a signal y, you multiply it by W1 transpose, which is equivalent to a convolutional dictionary transpose. You then add bias and apply ReLU, which is equivalent to soft non-negative thresholding with threshold beta 1. And then you repeat all the rest of the steps, which are again equivalent. So what am I saying? I'm saying that the layered thresholding algorithm and the forward pass of CNNs are equal. Or in other words, it means that you can interpret the forward pass of CNN as a very crude approximation of a sparse coding algorithm under this MLCSE generative model. Crude sparse coding. And what you can do with this is now actually use the theoretical study of sparse representation in order to explain certain things in deep learning. So let's, in order to understand what kind of questions you might answer, consider the following box. This box has again a button that whenever you press, you obtain a signal X which satisfies our assumptions. This is basically because this is a generative model. Now this X is contaminated with noise to create Y, which is fed into another box, which is called A. A is an algorithm, and this algorithm tries to estimate the underlying representations. For instance, using the layered thresholding, which is the forward pass, or maybe another algorithm. And now that we have this generative source model point of view, we can actually ask certain questions. For instance, can I guarantee under certain conditions that the estimates of the forward pass are guaranteed to be close to the underlying set of representations? Another question I might ask is, does this forward pass algorithm have certain limitations? If it has limitations, maybe we can propose different architectures. Maybe different architectures were already proposed. Maybe we can propose other different architectures. Maybe these were proposed also. And other questions that you might ask yourself is, how can you actually train the different dictionaries in different methods other than what CNN is doing? Or maybe you can provide some certain insights on how to operate on signals. Can you provide some insights on what different tricks are doing, batch normalization, dropout, etc. So I'll show you one theorem that we can prove, which says that if all the representation throughout the layers are all L0 infinity sparse, then the layered thresholding algorithm, which is basically the forward pass, is guaranteed to succeed in finding the correct supports and also finding representations which are close to the true ones. Which means that you can prove the stability of the forward pass under the assumption that all the representations are locally sparse, and also another assumption about the noise. And this theorem also sheds some light on some limitations of the forward pass. For instance, you can show that the assumption on the sparsity throughout all the layers relies on this term, this ratio, gamma min divided by gamma max. And this ratio basically measures what is the ratio between the minimal entry and the maximal entry in absolute value in the certain representation. If the representation have, for instance, plus 1, minus 1 coefficients, then this is 1. And you can see that basically the forward pass success relies on this. Another thing you can see is that there's a certain error growth. So if you actually look at these expressions I'm showing you here, you can show that the deeper you go with the layers, the higher the deviation between the true representation and the estimated one. And another thing that you can also show by looking closely at this theorem is that even if you add no noise to the signal and everything is supposedly perfect, this algorithm is never guaranteed to find the underlying representations. Again, because it's a crude sparse coding algorithm. So a natural question to ask is, can you actually tackle some of the limitations presented here? So you can. So again, our goal was to estimate the solution of this deep coding problem, which is depicted here. And we said, let's do it using the thresholding algorithm, which is the silliest possible approach. But you could do something which is much better. You could, for instance, take the signal y and estimate gamma 1 by solving a basis pursuit problem. For instance, using iterative thresholding, as Raju already mentioned. And then given the estimate gamma 1, you can solve for gamma 2 by solving another basis pursuit problem. And you can do this throughout all the layers. Now, the nice thing about, and this is connected to the conv networks, which is actually a work before. It's not that the convolutional layers, you guys are familiar from CNNs, it's actually a work before AlexNet. So the nice thing about the assumption of a generative model is that you can actually provide guarantees for certain algorithms, like we did for the forward pass, and you can do the same for the layered basis pursuit. So what you can show is that, again, if all the sparse representations are locally sparse, then this algorithm is guaranteed to perform well. And you can see from this theorem that certain problems that I previously mentioned are no longer problems. So for instance, there is no longer this ratio that appeared here previously, which means that you're not dependent on the contrast ratio in the representations. Also, you can show that there is no noise now, there is no error in the representation recovered if there is no noise added. So in simple words, this algorithm is guaranteed to successfully find the underlying representations if you don't add noise to the signal. And this problem of error growth, which we actually didn't solve here, we did solve in a recent work. So you can actually tackle all of these problems. Okay, so you might ask yourself at this point, great, so you're showing theoretical results that are supposedly claiming that this architecture is better than layered thresholding, but how can you actually implement this in practice? So the way to do it is to solve each basis pursuit problem using a certain algorithm. So imagine that you have this layered basis pursuit that iterates over the different layers J. And imagine that you use the iterative thresholding algorithm to solve each basis pursuit problem. So what you obtain is these certain architectures that has two loops. The first loop is over the iterations of the iterative thresholding algorithm, and the second loop is over the different layers. And this is basically a very deep recurrent neural network where these certain iterations in a certain abstraction level share the same set of dictionaries. And if you actually look at the architecture that you obtain from this layered iterative thresholding, it actually resonate. Okay, so what did we see today? We began by talking about the importance of models in signal image processing and talking in particular about the sparse length model. I then showed an extension of this model, which is called convolutional sparse coding, and a theoretical analysis for it. We then proposed a multilayer extension, which is called multilayer convolutional sparse coding, showing how it's connected to CNN and showing how you can use the insights from sparse representation to this model. And there are basically two take-home messages. The first is that generative modeling of data is actually a good idea because you can do two things. You can theoretically analyze certain algorithms, and you can actually propose systematically new algorithms like we did based on these theoretical insights. And the second take-home message is that the MLCSC model could be a new platform for understanding what CNNs are doing. Just one more thing, I would like to, I don't know what's the word for this. advertised, thank you. Miki Elad and Yaniv Romano are actually launching a massive online course on sparse representation these days. So if you guys would like to hear more about sparse representation, check it out. Thank you very much. You can come here to ask questions, if you have any.
So if there are any questions for any of the three of us, you can ask questions.
Hi. I wanted to ask you primarily the question of how do you learn the different level of dictionaries, and just like in CNN, how do you decide the number of levels to which you will have to go? Like, is it 5 layers or is it 5 levels? How do you decide on each of them?
Does this work? Yeah. Regarding the training of the dictionaries, there is essentially a spectrum of methods where on the one end of the spectrum you would have a SGD sort of training. You could basically say that SGD is some sort of a dictionary learning algorithm. Actually, not some sort, it is. And in the other end of the spectrum, you would see, for instance, more classical approaches for dictionary learning, such as KSVD, online dictionary learning, or whatever. So my answer would be you need to choose where you want to be in this spectrum. Do you want to do something which is closer to classical methods or to recent methods? And mathematically speaking, the main difference between the two is are you doing an end-to-end optimization or not end-to-end optimization? Or are you solving a bi-level problem or not bi-level problem? I can show you the math if you want. But basically, there is a certain spectrum between those two, and they're very related.
So my question is, basically, when you start with the level 1, you start with the images, and then you learn convolutional dictionary D1.
Yeah.
And in the next step, what are you using as your input to learn the next level of dictionary? Is it the sparse feature maps?
Yes.
The sparse feature maps.
Yeah. And the reason you do it because it has structure. You can view it, and it has actually patterns. Like you can visualize the sparse representation and see that it looks kind of like an image. No answer to that. Until your accuracy drops. It's a joke.
Regarding the global optimization problem, you said when you add more parallelism, you may obtain global optimum. But in that case, you change the network. So do you have any information or do we have any knowledge about if we knew the global optimum of the original network, that will have a performance? And for example, we had, before adding more parallel layers, if we had the opportunity to obtain the global optimum of the network, we will have a solution. Then we add parallel networks, and we have a global optimum. And do we have any comparison between the latent global optimum and the global optimum that we would have if you could find it? No? No.
So I'm not so sure I understand the question very well, so let me rephrase it the way I understand it. You could have a network, let's say AlexNet, and you're just trying to ask the question, do I get the global optimum for that network? The way we do things right now is by simply saying, well, if not, you just add a parallel subnetwork and you keep adding until you get 0 weights. And you could ask the question, well, maybe in the original network, there was a global optimum for that fixed size. So the technology we have doesn't allow you to find that global optimum for that fixed size as of yet. And the only existing results where you can do that are for the matrix factorization problem, where for every possible size, there is recent work from Joan Bruna saying that you can find the global minimum. So what you're asking of how do you guarantee global optimality either for fixed size or either by just modifying the network in many local ways, such as just adding a neuron in one particular layer as opposed to having to add a whole parallel subnetwork. That's very much open problem, and that is the open problem that I mentioned when I said that the work was restricted to one number for size and the addition of parallel subnetworks as opposed to adding an extra layer or adding an extra network, adding an extra neuron.
Your answer answered my first question that I had in my mind. And the second, but more generic, is there is this new area of research or work people are putting in to make neural networks learning more decisive, the traceability problem of decisions that neural networks take. Do you think any of these techniques can lead us to having more traceable determinism in the whole learning process?
I don't know exactly what traceability.
Let's say we are using one of these learned machines to identify cancer or make a decision in an autonomous car to turn left, right, or put a brake or something. Of course, there are errors in this. Now, these errors needs to be traced back to something. If it were to be a human, if it were to be a doctor, then you can trace it back to him and say, he didn't learn his school well. But we can't do that for the neural net. Are there any techniques that can be proven or could be cajoled up using any of these techniques that you have said?
Maybe we could make the network more robust to different errors. And so the reason I'm saying that is because in that case I do have an answer. So if you would like to make your network more robust to, let's say, adversarial examples or something like that, so there's a recent work of Perceval networks, and what they're doing, if you look at their way of regularizing the network, is actually equivalent to minimizing the mutual coherence, or something which is very similar to the mutual coherence. So in that respect, you could say that this leads to a more robust network that might not lead to the errors you're describing. But given an error, attributing it to, for instance, a certain atom in a dictionary, I'm not sure about that.
So to complement, I don't think we are in a position that this can be done generically for any problem. But it is possible to design architectures that are a little bit more interpretable. Concrete examples are that I know of, because we have worked on those, is if you're trying to do human activity recognition, then you can constrain the structure of the weight and the architecture to be dependent on human body parts. Okay. And even some of these dictionary learning methods, you can have one dictionary for each body part, for example. Therefore, then you can look at the weights, the largest weights, to figure out for this action, which ones were the body parts that were the most relevant for doing classification. And when there is a mistake, you can trace back the codes and they say, okay, this classifier of the wrist motion made a mistake. But generalizing from that to the more general traceability, I think my only answer is very generic, which is the more you understand what the networks are really doing and what their robust and stability properties, the better you can answer the question. But it's going to take time.
Yeah, but it's still based on some kind of decision tree that you would get with a number of these components of the machine.
Someone had raised their hand before you. I think it was you, yes.
Thanks. So in the last talk, you show the relation between multi-layer sparse coding and the convolutional neural network, and I expect that. But in the end, you show something like an iterative thresholding algorithm, and I would expect you would accelerate this algorithm by using the convolutional neural network, like in the second last talk. So is it straightforward or there is some issues to solve?
I could say it's straightforward, but you cannot say something straightforward before you implemented it. It sounds, okay, so from our experiments, we actually try to do things under certain model limitations to prove that what we're saying is correct. So, for instance, doing a lista in different layers would mean that you are not coupling these two matrices, right? You have I minus D transpose D, and you have the D transpose. So from my point of view, it's actually beneficial to couple them, because then you are doing proper iterative thresholding and proving that the model is correct. From a definitely is a strong word.
Just a simple question. You mentioned that AlexNet was approximately positive homogeneous. Why is it approximately?
Normalization.
The normalization part.
Oh.
Normalization. Okay,
Thank you.
no more questions. Thank you everybody for coming.